Hello there, and welcome to Science for Sleep, a quiet corner where we take the most intense questions the universe has ever created and wrap them gently enough for the mind to drift without strain. Tonight we're easing into a topic that sounds almost too extreme for a bedtime story, yet somehow becomes even more fascinating when spoken softly. It's something so far beyond any temperature you've ever felt, beyond the heat of stars, beyond the glow of fusion, beyond anything the universe can currently produce. It's the upper limit of heat, the point beyond which our physics falters so completely that it becomes difficult even to describe what's happening without the words tying themselves in knots. This is the Planck temperature, a place where the world behaves in ways so unfamiliar that our best theories stop cooperating and everything we know about matter and energy begins to warp, buckle, and give up its usual rules. Before we wander toward that impossible threshold, I want to know something simple about you. Where are you listening from tonight? And what kind of evening is unfolding around you as you settle in with this quiet curiosity? Some of you might be relaxing in a dim room. Some might be listening from a busy city that hasn't quite decided if it wants to sleep. And others might be somewhere peaceful with little more than the soft hum of night in the background. Wherever you are, I'm glad you're here, ready to explore something that pushes physics right up against its limit. If this gentle journey feels soothing or helps you find a bit of calm at the end of your day, I'd be grateful if you'd give the video a like or subscribe. It helps others find their way here, and you never know who might need a quiet moment to settle their thoughts. But let's ease forward now, because the Planck temperature isn't something to rush toward. It's a threshold that deserves slow steps, careful breaths, and enough space for the mind to settle into the idea piece by piece. There's no need to brace yourself. Despite the topic being the hottest temperature imaginable, nothing here will overwhelm you. We're moving through it gently, like turning the pages of a book that wants to be explored slowly. The Planck temperature sits at around 1.44168 x 1032 Kelvin. That number is so large it almost loses its meaning as soon as you try to say it. It's far hotter than the core of a supernova, hotter than colliding neutron stars, hotter than anything humans could ever hope to produce. It's the kind of temperature the universe only knew in its very first moments, when everything was compressed into an unimaginably tiny space, and the usual behaviors of matter had not yet settled into their familiar forms. When you hear a figure like that, you might expect it to be like other extreme numbers, something that simply stretches the scale further in the same direction. But the Planck temperature isn't just an extreme point, it's a boundary, a place where the equations themselves begin to fail, not because the math is flawed, but because the concepts we're trying to use were never designed to apply to something so intense. It's as if temperature itself starts to lose its meaning, and the energy of the universe becomes so compressed that the very structure of space begins to buckle. Yet we're not heading there with dramatic energy. We're approaching it at the softest pace, allowing the mind to get accustomed to the ideas without feeling like they're being hurled at it. Temperature in the everyday sense is simply a measure of how fast particles are moving. When you warm something up, you're essentially giving its particles more motion. They jiggle, collide, and rush around more intensely. At higher temperatures, the particles move faster, and at extremely high temperatures, they can move at speeds nearing the speed of light. But there's a limit hidden in that simple picture. Nothing can move faster than light. So if temperature is tied to motion, and motion can't exceed that ultimate speed, temperature hits a conceptual wall where giving the particles any more energy doesn't make them move faster in the way we usually imagine. Instead, that extra energy has to go somewhere else. This is one way to begin thinking about why the Planck temperature is so strange. It's the point at which the usual notion of motion breaks down, and energy stops behaving like something that can simply be added to a particle without changing the nature of the space around it. The moment we get close to this temperature, quantum mechanics and general relativity start arguing with each other. Normally, we keep their disagreements neatly separated. Quantum mechanics rules the tiny scales of particles and probabilities. general relativity rules the large scales of planets, galaxies, and gravity shaping space. They coexist peacefully most of the time because their territories don't overlap very much. But at the Planck temperature, everything happening is so incredibly energetic and so incredibly small that the rules of the tiny and the rules of the massive collide head-on. They're forced to exist in the same situation, and they don't agree on what should happen. The universe as we know it doesn't offer a unified explanation at this scale, which means describing what happens there involves a kind of careful speculation based on the best clues we have. Yet there's nothing frantic about that uncertainty. It's more like standing at the edge of something we can sense but not quite articulate, and letting the unknown be part of the calm rather than something to hurry through. Imagine trying to describe a familiar object, like a table, while wearing a pair of glasses that show you two completely different images overlaying each other. One lens shows the table as a smooth surface made of solid wood. The other lens shows the same table as a buzzing cloud of particles with empty space between them. Now imagine that at the Planck temperature, both lenses try to dominate the picture at once. They're both accurate within their own domains, yet the two perspectives cannot be combined without producing distortions. That tension is at the heart of why the Planck temperature is so complex. Our tools for describing reality weren't made for this environment. But in a quiet setting like this, the strangeness doesn't feel stressful. It feels like something you can sit with, something to observe without needing a perfect answer. As the temperature approaches the Planck scale, energy becomes so concentrated that space itself becomes unstable. The smooth fabric we're used to describing with relativity begins to vibrate and fluctuate in ways that resemble the unpredictable behavior seen in quantum mechanics. The surface of reality, if you want to think of it that way, stops appearing flat or curved and instead begins to froth with tiny, rapid fluctuations, sometimes called quantum foam. These fluctuations are so small and so short-lived that they can't be directly observed, but their existence is suggested by the mathematics of quantum field behavior at extremely tiny scales. The Planck temperature pushes that foam into a level of intensity where the smoothness of space is overwhelmed completely. Rather than a steady surface, space becomes something far more active and unpredictable. But for us, talking about it here in this peaceful moment, the intensity becomes something to examine slowly and patiently, letting the imagination form the idea in a way that doesn't overwhelm the senses. Another way to approach the idea is to think about how forces behave at lower temperatures. In our everyday world, we have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They act differently, have different strengths, and each follows its own rules. But as the universe gets hotter, these forces begin to blend together. At extremely high energies, some of them unify, behaving as different aspects of the same underlying interaction. As you continue pushing upward toward the Planck temperature, more of these distinctions blur. By the time you reach this final limit, every force is expected to merge into a single fundamental interaction. Everything becomes unified in a way that we can only approximate with theory. And while that may sound dramatic here in this quiet moment, it becomes another gentle step into understanding the nature of the universe. There's no rush to solve it, just a slow unfolding of what the physics suggests. At this peak temperature, if we try to assign meaning to the word temperature at all, the energy density becomes so high that any attempt to measure or localize that energy would create a gravitational field strong enough to collapse into a tiny black hole. That means even trying to observe the situation directly would change it so dramatically that the act of measuring destroys the structure you're trying to measure. It's a bit like trying to examine the surface of a soap bubble using a tool that pops the bubble the instant it gets close. That limitation tells us that the Planck temperature is less of a physical state we could ever reach, and more of a boundary that marks where our understanding stops working. Yet thinking about that limitation doesn't need to feel frustrating. Instead, it becomes a reminder that the universe has depths that invite exploration without demanding perfect clarity. The early universe passed through this temperature in less than a fraction of a second. It was so brief that even calling it a moment feels almost too generous. But that tiny interval left clues scattered throughout the structure of the cosmos. The distribution of galaxies, the shape of the cosmic microwave background, and the behavior of matter under extreme conditions all hint at the physics that operated long ago. We study these clues not just to understand the past, but to understand the boundaries of physical law. In this quiet space right now, those clues feel less like a complex puzzle and more like stepping stones, each one offering a small insight into something unimaginably intense, but still approachable with a calm mind. Nothing we do in a laboratory can reach the Planck temperature. Even the most powerful particle accelerators fall inconceivably short, and even if they could push energy levels that high, the conditions would be impossible to sustain or observe. That means the Planck temperature is a theoretical marker, something defined not by direct measurement but by the limits of our equations. It's like a horizon that moves whenever you try to get closer, not because it's avoiding you, but because the tools you're using stop being useful in that domain. Instead of trying to force those tools where they don't belong, we treat this boundary as a guide, letting it tell us where new physics must eventually take over and where future theories must fill in the gaps left by the old ones. And in a way, that gentle acknowledgement that we don't yet know everything becomes part of the comfort. There's no pressure to understand it all at once. There's simply an invitation to keep learning at whatever pace feels right. Heat is something we think we understand because we experience it constantly in ordinary life. A warm mug in your hands, the sun on your skin, the air from a heater drifting slowly across a quiet room. All of those feelings come from the same basic idea: particles moving faster and transferring their motion to whatever they touch. But the moment we start walking toward levels of heat far beyond anything we could ever encounter, the picture begins to shift in ways that don't line up with those familiar experiences. There comes a point where heat stops being something that makes things hotter in the traditional sense, and instead becomes something that transforms the very rules those particles follow. It's not a matter of fire or flame anymore. Long before reaching anything close to the Planck temperature, heat becomes something deeper, something that changes from a sensation into a state of reality. As temperatures climb, the energy stored in particles grows. At first, this simply means atoms vibrate more quickly. Increase the temperature further, and those vibrations tear atoms apart. Keep raising it, and even the nuclei at the centers of atoms can fall apart. At extremely high temperatures, matter becomes a plasma, a state where electrons no longer stay bound to their nuclei, and everything becomes a sea of charged particles rushing freely. Many stars, including our sun, glow and behave this way, but even that isn't unusual compared to what lies beyond. Once you approach temperatures far above what stars reach, you begin to enter a region where protons and neutrons themselves lose their identities, dissolving into their component quarks and gluons. That state is known as quark-gluon plasma, and it's one of the hottest forms of matter ever recreated on Earth, albeit only for incredibly short periods of time in particle colliders. Even then, the temperature achieved is an almost insignificant fraction of what lies between that and the Planck temperature. In this range of early transformations, heat is still something we can describe with the tools of particle physics. Quarks move around freely. Gluons, the carriers of the strong force, behave differently than they do inside protons and neutrons. Everything becomes a dense, energetic fluid that behaves almost like a perfect liquid with extremely low viscosity. The experiments that produce it show that it flows more smoothly than water. That's already unusual, but nothing here fully breaks our understanding. It stretches it, but it doesn't shatter it. We know how to describe these interactions with quantum chromodynamics, the theory that governs the strong nuclear force. But this is only the beginning of how heat transforms into something stranger. As temperatures continue to rise in theory, something unexpected happens. The familiar distinctions between different fundamental interactions fade. Forces that seemed separate begin to resemble each other. At lower energies, electromagnetism and the weak nuclear force appear different. They act differently and affect matter in separate ways. But at extremely high temperatures, long before we reach the Planck limit, these two forces merge into a single unified interaction. It's not a matter of interpretation or speculation. The mathematics describing the electroweak theory show that, above a certain temperature, the symmetry between the electromagnetic and weak forces is restored. The universe itself once passed through such a phase when it was young. At that time, there was no difference between electromagnetism and the weak force. Everything operated under one framework. This marks an important shift. Heat has moved from simply causing matter to change into new forms to something that alters the underlying interactions themselves. What we call temperature is now directly tied to features of reality that aren't just about vibrating particles, but about the structure of the laws that govern those particles. This is where heat becomes something that goes beyond fire or energy in the everyday sense. It becomes something that influences the behavior of nature at a fundamental level. Moving further upward along this scale, we encounter increasingly theoretical territory. We know certain unifications occur because the mathematics of established theories demand them. But beyond that, predictions rely more heavily on frameworks that push the boundaries of what we can confirm. At these even higher temperatures, well beyond anything electroweak unification can explain, the strong force is expected to merge with the electroweak interaction, forming a larger unified force. Several models propose that all forces except gravity combine at this stage. Others suggest different variations depending on the pathways the universe may have taken during its earliest moments. But what all these ideas share is the understanding that high energy smooths out the distinctions between interactions that seem unrelated under normal conditions. This shift is one of the best illustrations of how heat becomes something stranger than fire. In everyday experience, heat affects the motion of particles, changes states of matter, and influences chemical reactions. But these temperatures reach far beyond the domain of chemistry or even nuclear physics. They enter a realm where the concept of separate forces loses its meaning. What appears to us as multiple forces may just be different manifestations of the same underlying interaction at lower energies, and as you move up the temperature scale, you're essentially peeling back layers of symmetry, breaking that hide, that unity. It becomes worthwhile to examine what temperature really means in this context. Temperature is often defined as the average kinetic energy of particles, but when you reach these levels, describing it as motion becomes less useful. The energies involved are so high that the particles cannot simply move faster in the way we normally imagine motion. They approach speeds limited by the structure of space-time, and extra energy changes the nature of the particles themselves. At a certain point, the idea of treating particles as small objects with defined identities becomes less effective. Instead, quantum fields become the primary description. And now, heat is something that excites these fields to such an extent that their usual behavior becomes distorted. As temperatures climb further, the energy becomes so intense that any small region containing it would create a gravitational field noticeably stronger than anything found even near neutron stars. This is still far below the Planck temperature, but it shows how the concept of heat has started linking to gravity in a way that doesn't occur at ordinary temperatures. Normally, we don't think of heat as something that influences gravity. The energy of thermal motion does contribute to gravity because of the relation between energy and mass, but the effect is tiny and negligible in daily life. At much higher temperatures, however, this contribution becomes significant. The thermal energy is so large that its gravitational influence can no longer be ignored. In principle, enough concentrated heat could warp the curvature of space in observable ways. This subtle shift foreshadows what will happen when energy reaches levels so extreme that space-time itself can no longer be treated as a smooth background. Heat in this range affects everything at once. It reshapes interactions, influences space-time, and forces every type of particle into conditions where their usual distinctions fade. even photons, which behave predictably at lower energies, begin to act differently. Their contributions to the energy density enhance the overall gravitational effects in ways that push the structure of space-time toward instability. While all of this occurs at temperatures far below the Planck limit, it demonstrates how heat has ceased to be simply a measure of motion and has become a driver of structural transformation. The universe experienced these conditions during its earliest moments, and the traces of those conditions still linger. The uniformity of the cosmic microwave background radiation, the distribution of galaxies, and the spread of matter throughout the universe all reflect transitions that occurred while temperatures were unimaginably high. Those transitions shaped how the universe expanded, how matter formed stable structures, and how the forces separated. So in a sense, exploring what heat does at these extreme levels is also a way to understand why the universe looks the way it does today. Another interesting point to consider is that heat at these scales no longer behaves linearly. Adding more energy doesn't simply scale up the effects you saw earlier. Instead, new phenomena appear abruptly. Symmetries that were broken at lower energies are restored. Particle masses shift. Some interactions vanish, while others become dominant. It's not a smooth extension of everyday heating. It's more like entering new regimes of behavior each time the temperature crosses a certain threshold. These thresholds represent boundaries where the physics changes form, and each boundary reveals something new about how reality organizes itself. As you rise even closer to the Planck scale, the idea of temperature becomes harder to define. Normally, temperature requires that particles exist in a system long enough to reach equilibrium. They need to exchange energy consistently, but at the highest temperatures in the early universe, equilibrium becomes questionable. The energy density and rapid expansion meant conditions changed faster than particles could settle into a stable distribution. If you were to place a thermometer in such an environment, the concept of measuring heat wouldn't work the same way it does in a controlled system. It's not that the thermometer would melt, it's that the very assumptions behind what a thermometer measures would break down. At temperatures heading toward the Planck scale, even fields that appear stable at lower energies begin to behave unpredictably. Quantum fluctuations grow stronger, making space-time jitter in ways that challenge the idea of a smooth geometry. In normal physics, we treat space as a continuous background, but at these temperatures the fluctuations become so pronounced that the usual geometry no longer holds. Distances blur, durations lose consistency. These shifts are not abstract. They reflect real changes predicted by attempts to merge quantum mechanics with gravity. When seen from this perspective, heat becomes something that rewrites the framework within which particles and forces exist. It ceases to be a simple input of energy into a system and becomes a means through which the rules of that system reveal their underlying unity. There's no point at which this transformation feels sudden or abrupt in the calm way we're talking about it now. Instead, it unfolds gradually as temperatures increase, each step showing a new behavior that wasn't visible before. When we start shrinking our view smaller and smaller, there comes a point where ordinary language begins to lose its usefulness. Most people can imagine a grain of sand, and most can imagine something smaller than a grain of sand. But once you move far beyond that, the mind starts reaching for comparisons that no longer help. Human hair is already thin enough that you don't really think about its width unless you're looking at it under magnification. A red blood cell is smaller still, and the molecules inside that cell are so tiny that even seeing a diagram of them can feel strangely disconnected from anything physical. But as the scale continues downward, we reach a realm where even the idea of size starts to behave differently. The world becomes so compressed that our usual understanding of what it means to measure anything becomes strained. The smallest meaningful scale we can currently describe in physics is the Planck length, which is about 1.616 x 1035 meters. This is a distance so tiny that if you took something as large as a single proton and tried to compare the two, the difference would be almost as vast as the difference between that proton and the size of a star. The gap is immense in both directions. The Planck length isn't small in the way that a grain of dust is small. It's small in a way that challenges the very concept of a point in space being closer or farther from something else. At such a scale, space stops being smooth and begins to show signs of irregular, fluctuating behavior that doesn't fit the classical picture of geometry. To appreciate why this scale is so important, it helps to think about how we normally describe distance. We imagine measuring a length with some kind of tool, whether it's a ruler, a laser, or something more sophisticated. But measuring anything requires interacting with it. You have to bounce light off an object or place a probe near it. And when you interact with something at smaller and smaller scales, the interaction itself becomes significant. For example, shining light on something to see it means using photons. The shorter the wavelength of light, the more precisely you can locate the object. But shorter wavelengths come with higher energy. At some point, the energy of the photons you're using becomes large enough to disturb what you're trying to observe. The act of looking changes the situation so dramatically that the measurement loses its meaning. If you push this idea far enough, you reach the Planck scale. Here, the energy required to probe the distance is so huge that concentrating it in a small region would create a gravitational field strong enough to distort space-time. Instead of revealing what's there, the measurement collapses into something dramatically different. It's like using a tool that breaks the surface you're trying to examine, not because the surface is fragile, but because the tool itself disturbs the entire environment. This limitation suggests that the Planck length represents a fundamental limit to how finely space can be probed. It may not be that space stops existing below that scale, but rather that the concept of distance doesn't make sense in the usual way. It's a boundary where our current theories lose their ability to describe what is happening, not because the situation is chaotic, but because we don't yet have a framework that unifies quantum mechanics and gravity. Thinking about the smallest scales also leads us toward an understanding of why the Planck temperature is so unusual. At extremely tiny scales, quantum fluctuations dominate the behavior of fields. These fluctuations are always present, even in what we call empty space. They're small ripples of energy that appear and disappear continuously. At larger scales, these fluctuations average out, giving us the impression of a smooth, stable world. But near the Planck length, the fluctuations become more significant. Space and time themselves begin to appear irregular. Some theorists describe this unpredictability as quantum foam, a term that might suggest randomness or a frothy surface. But in this context, it simply reflects the idea that the geometry of space cannot remain smooth when probed at such tiny distances. One way to picture this is to imagine zooming in on a calm lake. From far away, the surface appears flat and calm. As you approach, you begin to see small ripples. Zoom in further, and you notice many more details, tiny shifts and disturbances that weren't visible before. At the Planck scale, the ripples are so intense and so numerous that the idea of a flat surface vanishes entirely. You can't describe the surface as smooth or wavy because those concepts no longer apply. The same happens with space-time. It stops behaving like a continuous medium and transforms into something fluctuating and unpredictable. But there's no sense of chaos in the way we're describing it here. It's more like becoming aware that the world has a level of detail that the human mind isn't naturally equipped to visualize. Quantum mechanics plays a major role in shaping how we understand the smallest scales. In that framework, particles are not tiny beads or dots, but excitations of fields. Each field fills the entire universe, and particles are localized vibrations in those fields. A photon is a vibration of the electromagnetic field. An electron is a vibration of the electron field. Rather than thinking of the universe as being made of small pieces, it's more accurate to say that it consists of layers of interacting fields, each of which can carry energy in discrete quantities. When discussing tiny scales, the uncertainty principle also becomes important. It tells us that certain pairs of quantities, like position and momentum, cannot be known simultaneously with perfect precision. At large scales, this doesn't matter much. You can measure the position of a car and its speed without worrying about the uncertainty. But at extremely small scales, the uncertainty principle has enormous effects. It means that the smaller the region in which you try to confine something, the greater the uncertainty in its momentum. This increased uncertainty leads to fluctuations in energy, and when the fluctuations become large enough, they can generate temporary particle-antiparticle pairs that appear and disappear rapidly. At the Planck scale, these fluctuations become so intense that the energy they represent would significantly curve space-time. The geometry is no longer merely influenced by matter and energy. It is constantly being reshaped by the fluctuations themselves, which leaves us without a clear picture of what the structure of space is. This is one of the central issues in trying to unify quantum mechanics and general relativity. General relativity describes gravity as the curvature of space-time, while quantum mechanics describes everything in terms of fields and probabilities. When both effects are strong, neither theory is sufficient on its own. They both provide partial descriptions, but they don't fit neatly together. Exploring these small scales doesn't require rushing toward a conclusion. Instead, it allows us to appreciate the gradual transition from the familiar to the unfamiliar. Starting from everyday objects and shrinking our perspective slowly makes it easier to see how each step leads to a new regime. At first, the atomic world appears strange but understandable. Electrons occupy orbitals rather than orbits, and atoms bind together by sharing or exchanging electrons. This might feel unusual, but the basic ideas remain accessible. It's only when you move deeper, into the realm of quarks, gluons and quantum fields, that the world begins to behave in ways that resist simple description. Shrinking even further allows us to appreciate why the Planck length is so significant. It is the scale where our current understanding stops being simply stretched and instead breaks down entirely. But this doesn't feel like hitting a wall. It feels more like reaching the edge of a map that has been carefully drawn, with detailed landmarks and familiar roads, and finding that beyond that point the landscape continues, but the map stops covering it. You know there is more there. You know it connects to what came before, but you don't yet know how to describe it in a way that fits the rest of the map. The Planck time, which is the time it takes for light to travel one Planck length, is similarly tiny. It marks the smallest meaningful interval of time as far as we know. Trying to describe events that occur over shorter periods fails for the same reasons that describing distances shorter than the Planck length fails. The fluctuations become too intense. The geometry becomes unstable. Time can no longer be treated as a smooth progression of moments. Instead, it becomes subject to the same irregularities and fluctuations that affect space. There is an intriguing implication here. If space and time lose their usual meaning at these scales, then the structure of reality is not continuous. It behaves as though it has a granularity, not because space is made of discrete pieces, but because the fluctuations make it impossible to define positions and moments more precisely than these fundamental limits. This granularity emerges not from the universe being built from blocks, but from the limits of measurement imposed by the laws of physics. The smallest scales we can imagine are not merely tiny versions of the world we know. They are fundamentally different. Everything about the familiar world, from the shape of objects to the motion of particles to the behavior of forces, changes character. It's not that space becomes chaotic. It's that the tools we use to describe it need to be replaced with ones capable of capturing the complexity of these fluctuations. This journey toward the smallest scales doesn't leave us with a neat picture. Instead, it opens up new questions, more possibilities for understanding how the universe behaves beneath the level of the particles we study. Temperature is one of those ideas that feels simple at first because we grow up experiencing it constantly. A warm day, a cold drink, a cozy blanket, a stove that gets too hot if you touch it for more than a second. From an early age, you learn that heat rises, cold sinks, metal conducts warmth quickly, and water needs a certain temperature to boil. These everyday experiences shape our intuitive sense of temperature. We think of it as something that increases when energy increases, something that changes matter from one state to another, something that makes molecules move faster or slower, depending on how much heat is present. But there comes a point where that simple connection breaks down, when the energies involved become so high that the movement of particles no longer follows the basic rules we expect. Temperature stops correlating with motion in the familiar sense. It stops behaving like the temperature we use to describe weather forecasts or kitchen instructions or the warmth of sunlight on your face. To see how this shift begins, imagine continuing to heat a gas. At first, its molecules move faster, they collide more frequently, spread apart, and exert more pressure. These relationships are described by equations we learn in school, equations that work perfectly well at normal temperatures. Increase the heat further, and the molecules eventually break apart into atoms. Keep raising the temperature and those atoms start losing their electrons. Everything becomes a plasma. So far, none of this challenges our understanding. It simply pushes it to more energetic levels. But if you keep adding heat past the familiar ranges, something begins to happen that isn't just an extension of the same story. The energy becomes so high that many assumptions built into the classical definition of temperature no longer hold. Ordinary temperature is defined statistically. It assumes a huge number of particles exchanging energy randomly until they settle into a distribution where some move faster, some slower, but the average reflects the temperature. This concept only works when the system is large enough and interactions are gentle enough that this sort of equilibrium can form. At very high temperatures, especially those relevant to the early universe or theoretical extreme environments, equilibrium becomes difficult to maintain. The rate at which particles interact and exchange energy may not keep up with the changing conditions. If the energy density is rising rapidly, or the environment itself is expanding quickly, the system never settles into the kind of stable distribution required for a traditional definition of temperature. One of the challenges of describing extremely high temperatures is that particles approach the speed of light. The energy added to them no longer increases their speed in the usual way, because they cannot exceed that fundamental limit. Instead of making them move faster, the extra energy starts altering their mass-energy relationship through relativistic effects. A hotter gas of particles begins to behave differently than expected, because the motion cannot continue to scale upward in a simple way. Particles acquire more energy but not more speed. That alone suggests that temperature eventually stops aligning with their motion. It becomes instead a measure of energy per degree of freedom, which is a more abstract quantity. But even that description starts failing once the energies become high enough. Eventually you reach a point where trying to define temperature using particle motion becomes misleading. Very high energy particles don't form stable distributions. Their interactions are so violent that the system doesn't behave like a gas anymore. Instead, the concept of thermal motion becomes tangled with field excitations that do not settle into neat patterns. At this stage, heat cannot be described as something that increases molecular motion. There may not even be molecules left. Instead, what exists are elementary fields being pushed into states where their usual low-energy approximations don't apply. You no longer have matter being heated. You have underlying quantum fields being driven into extreme conditions. Another reason temperature stops behaving normally comes from relativity. At high enough energies, the energy of a single particle becomes comparable to the rest energy described by mc2. This means the distinction between mass and kinetic energy becomes less meaningful. The temperature is now tied not only to motion but to the very identity of particles. As you heat the system, new particles can spontaneously form from the available energy. Temperature doesn't just change motion, it creates matter. At even higher energies, particles may lose their unique properties. Mass differences shrink. Distinct identities fade. The energy is so intense that the typical features distinguishing particle species become irrelevant. When adding heat changes what exists rather than how it moves, temperature begins to take on a different meaning entirely. The early universe passed through a phase where temperature had this unusual character. During its first fractions of a second, temperatures were so high that conventional matter couldn't exist. Instead of atoms or protons or electrons, there were only fields interacting in chaotic, high-energy ways. The idea of temperature still applied in a broad sense, but it didn't describe anything like the heat we experience today. It was simply a way to describe how much energy existed in each part of the space that was rapidly expanding. Even then, that description was approximate. The universe was changing so quickly that equilibrium may not have fully formed. If equilibrium didn't form, the normal relationship between temperature and motion would not have existed. As temperatures climb toward the range where forces unify, another strange effect occurs. At everyday temperatures, the electromagnetic, weak, and strong interactions all behave differently. They have different strengths and structures, but at extreme temperatures, these separate forces begin to merge. Their distinctions are caused by symmetry breaking at lower energies. When the temperature is pushed high enough, those symmetries are restored. This means that what we call a force at one temperature is not the same thing at another. In daily life, heating something doesn't change the fundamental forces acting within it. But at ultra-high temperatures, heat affects how the universe's forces behave. It influences the symmetry structure underlying all interactions. Temperature becomes not just a description of particle motion or energy, but a description of the universe's underlying framework. When the electroweak symmetry is restored, the photon and W and Z bosons become indistinguishable. Their unique properties fade, replaced by a unified behavior that only emerges at high temperatures. If you heat the system further, theories predict additional symmetry restorations. Depending on the details of various theoretical models, the strong force may unify with the electroweak interaction. This means temperature doesn't merely excite particles, it reshapes the structure of interactions themselves. Every increase in heat opens a new regime where the rules of physics shift. That alone is enough to show that temperature at these scales is not a simple extension of everyday temperature. It has transformed into something deeper. A further complication is that at extremely high temperatures, the energy density becomes enormous. Normally, we calculate temperature independently of space-time curvature, but energy contributes to gravity. When temperatures reach levels where energy density begins curving space-time in noticeable ways, the concept of temperature begins merging with gravitational effects. You can no longer treat heat as a property of particles alone. It becomes a property of the geometry itself. This sets the stage for even stranger behavior, because extreme curvature of space-time interferes with quantum interactions. The smallest fluctuations in fields become amplified by gravity. This interplay makes the system so unstable and unpredictable that defining temperature precisely becomes difficult. As temperature continues rising, the energy carried by each particle becomes so immense that any attempt to confine the system would create conditions resembling tiny black holes. If you tried to define temperature locally by measuring energy in a small region, the gravitational influence of that energy would collapse the measurement area. That doesn't mean black holes appear everywhere at those temperatures. It means that traditional measurement methods based on localizing energy become ineffective. The system cannot be treated as a gas or fluid anymore. Temperature no longer acts as a measure of average kinetic energy. It becomes tied to gravitational instability. This shows how deeply temperature has diverged from its usual meaning. As energies approach the Planck scale, the equations underpinning our descriptions begin to break. They don't fail because of arithmetic issues, but because the concepts themselves stop functioning properly. Quantum mechanics relies on probabilities and wave functions defined on a background geometry. General relativity describes how that geometry changes in response to mass and energy. At the Planck scale, the energy in each tiny region is high enough to distort the geometry, which then affects the quantum fields, which then alter the geometry again. This feedback loop cannot be captured by either theory alone. Because of this, temperature near the Planck scale cannot be described with the tools we usually use. The The definition of temperature relies on assumptions about equilibrium and defined geometry, both of which fail in this regime. If a system cannot reach equilibrium because interactions occur faster than thermalization, temperature becomes an approximate measure rather than a strict one. This is not unlike trying to measure the temperature of boiling water while it is being poured rapidly between containers. The concept of temperature still applies, but only loosely. At extreme energies, the system is in constant flux. Fields fluctuate so wildly that temperature becomes more of a description of the energy scale rather than the state of the particles. One important shift is that temperature begins to refer not to the motion of particles, but to the energy scale where different behaviors emerge. In particle physics, increasing the temperature means increasing the energy scale of interactions. Instead of thinking about motion, you think about how energy changes the behavior of forces. In this sense, temperature becomes a label for regimes of physical behavior rather than a measurable property of matter. At one scale, atoms form. At another, nuclei form. At another, quarks exist freely. And at another, forces unify. Temperature describes which interactions are relevant, not how warm something feels or how quickly particles move. Another way to see how temperature stops acting normally is to consider that at ultra-high energies, the number of available states for particles changes. Particles can become effectively massless. Others may acquire mass through mechanisms tied to symmetry breaking. These changes alter the relationship between energy and temperature. The system may require enormous amounts of added energy to raise the temperature by a small fraction, simply because the newly accessible states absorb that energy. Temperature becomes decoupled from the straightforward idea of heating. For example, when the universe cooled through the electroweak phase transition, the temperature dropped but the energy density remained high, because a portion of the energy contributed to symmetry breaking rather than to particle motion. This is the reverse of what we normally expect from everyday heating or cooling. Heat stopped behaving like heat. It became a way to track which symmetries were active. Instead of affecting movement, it affected the structure of the laws themselves. As the temperature rises further, fields that are normally stable begin to fluctuate strongly. The vacuum itself becomes unstable. This is not instability in the sense of an object falling over. It refers to the underlying state of the fields that define how particles behave. At extremely high temperatures, the vacuum can shift into alternative configurations. Temperature becomes tied to transitions between these configurations. The familiar relationship between heat and motion is not relevant here. It has been replaced by a relationship between heat and the structure of reality at its most basic level. There comes a point in the journey toward higher and higher temperatures when the familiar behavior of matter has already dissolved. Atoms vanish first, followed by nuclei, followed by any stable collection of quarks or leptons. Long before reaching the uppermost temperatures, each familiar structure breaks apart because the energy becomes too high for anything stable to remain intact. But even after passing the temperatures where matter as we know it ceases to exist, you can still talk about particles and fields behaving according to the theories we rely on. Those theories stretch, contort, and carry us surprisingly far. Yet eventually, there is a level of heat that forces the entire framework to falter. It is the point where our descriptions stop matching the behavior of reality. This is the threshold where the theories we depend on begin trembling under pressures they were never built to withstand. Reaching this threshold doesn't happen suddenly. It is a gradual process where small cracks first appear in the assumptions behind our equations. At lower temperatures, quantum mechanics functions comfortably, describing particles as excitations of fields in a smooth space-time. General relativity also works well at ordinary densities, presenting gravity as curvature of space-time that responds to energy and mass. The two systems operate independently most of the time. You never have to worry about general relativity when calculating the behavior of an electron in an atom. Likewise, quantum mechanics is irrelevant when describing how planets orbit stars. Each theory rules its domain without conflict. As temperature rises, however, these domains begin to overlap. The energy density becomes high enough that the mass energy of particles significantly affects gravity. At the same time, the tiny scales involved mean quantum fluctuations become enormous. These two influences clash. Gravity wants to describe space-time as smooth, but curved. Quantum mechanics insists that at extremely small scales, fields fluctuate violently. Neither description can accommodate the demands of the other. This tension grows stronger with each increase in energy until it becomes clear that neither theory can be stretched any further. To see how this conflict emerges, consider how temperature affects energy density. At everyday temperatures, the energy stored in thermal motion is insignificant compared to the mass of objects. It has no measurable effect on gravity, but as the temperature climbs, the thermal energy per unit volume increases rapidly. Eventually, the energy becomes large enough to produce noticeable curvature in space-time. At these temperatures, you can't describe particle motion purely with quantum mechanics because the background space itself is shifting. But using general relativity alone also fails because the small-scale fluctuations of quantum fields disrupt the smooth space-time needed for Einstein's equations. The theories interfere with each other instead of supporting one another. Another difficulty arises from the way quantum field theory treats energy. In quantum mechanics, energy is quantized, with fluctuations allowed even in empty space. These fluctuations become more intense at smaller scales. When the temperature approaches extreme levels, the fluctuations can be large enough to influence space-time curvature. The geometry begins to respond to these variations, creating distortions that alter the behavior of the fields. But once the geometry responds, the fields change again. You end up with a feedback cycle that normal calculations cannot contain. The linearity and smoothness that quantum field theory assumes no longer apply. Temperature also affects particle identity in this range. The masses of particles are not fixed quantities. They arise from interactions with fields such as the Higgs field. At high enough temperatures, the Higgs field loses its usual configuration, making particles effectively massless. The mass differences between particle types shrink. Thermal energy dominates everything. The idea of distinguishing between particles becomes less meaningful. When a particle's identity fades, the usual interactions no longer behave according to the low-energy rules. Heat merges them into simpler patterns that only appear at extreme temperatures. The trembling of physics doesn't mean the world becomes chaotic. It means our tools were not designed for these extreme conditions. Each theory gives predictions that contradict each other. For example, quantum field calculations predict infinite values for energy density at extremely small scales if carried out without modification. These infinities hint that the theory is incomplete. Renormalization techniques can remove some infinities, but only up to a point. As you drive the system toward the Planck scale, the remaining infinities become unavoidable. They aren't mathematical errors. They reflect that the theory doesn't apply in this domain. General relativity faces its own limits. The curvature of space-time can grow arbitrarily large in Einstein's equations. Nothing prevents that mathematically. But quantum mechanics implies that the curvature cannot be known precisely, and certainly cannot reach infinite values, because fluctuations dominate the behavior at small scales. Relativity treats space-time as continuous and differentiable. Quantum mechanics treats everything as subject to uncertainty and fluctuation. These two views collide so violently at high temperatures that trying to fuse them without a new theory leads to contradictions. The early universe approached this trembling threshold during its first tiny fraction of a second. All forces except gravity were expected to unify, and the thermal energy density was immense. But gravity was still too weak to unify with the others, at least according to our current understanding. The energy scale where gravity merges with other forces lies at or near the Planck scale. Below that scale, gravity is comparatively weak. Above that scale, we cannot use current theories to describe what happens. The trembling occurs because the universe was nearing a point where none of the separate theories were sufficient. One can also see the trembling in the behavior of particles as they interact. At extremely high temperatures, Scattering events occur with such enormous energy that the cross-sections predicted by quantum field theories begin diverging. You get paradoxical results. Interaction rates may grow faster than they are supposed to. Particles may appear to acquire energies that would distort the space-time around them. Virtual particles can appear with energies so large they influence gravity in significant ways. Both quantum mechanics and relativity impose limits that become incompatible at these energies. Temperature in this regime becomes inseparable from space-time geometry. Heating a system changes the geometry. Changing the geometry changes the interactions. Interactions alter the energy density. The feedback loop makes it impossible to treat any part of the system independently. Physicists refer to this as reaching the region where quantum gravity effects become unavoidable. But since we do not have a complete quantum gravity theory, this threshold marks the end of where our current descriptions can be trusted without reservation. When we describe this trembling, it's not a literal vibration or shaking. It's a metaphor for the structural instability in the theories themselves. Equations yield contradictions. Predictions diverge. Quantities skyrocket toward infinities. Symmetries that should remain break down unpredictably. Even the vacuum behaves differently. At lower energies, the vacuum is a stable background state. At high energies, the vacuum is filled with intense fluctuations that distort space-time. The distinction between empty space and matter narrows. Everything becomes a seething environment of energy. This region also reveals something about the limits of temperature itself. Before reaching the Planck scale, temperature can still be defined in terms of an equilibrium distribution, even if the equilibrium is temporary. But as energy rises, equilibrium stops forming. The scattering events occur so rapidly and with such high energy that the system cannot settle into a stable state. Temperature becomes a rough approximation rather than a definite quantity. It describes the scale of the energy rather than a precise thermodynamic condition. Another sign that physics begins to tremble is that the forces acting in the system lose their separate identities. At lower energies, forces behave differently. Gravity curves space-time. The electromagnetic force influences charged particles. The strong force binds quarks. The weak force governs radioactive decay. But at high energies, some of these differences vanish. Forces merge. Interactions become simpler. Temperature becomes a marker for which version of the forces applies. Heat no longer changes motion. It changes which laws of physics are active. That shift represents an enormous conceptual transition. Even the concept of dimensionality undergoes stress in this environment. Some theories suggest that at very small scales, space-time may have fewer effective dimensions. Others propose extra dimensions compactified so tightly that they only reveal themselves at high energies. Temperature has the potential to awaken behaviors tied to these extra dimensions. But because our theories are incomplete, we cannot determine exactly what happens. The trembling arises from the uncertainty in the structure of reality. Heat pushes the system toward regions where new dimensions might become relevant, where forces unify, where fluctuations dominate, where space-time geometry no longer behaves as a passive backdrop. There is also the issue of energy localization. To measure temperature or interactions at extremely small scales, one must concentrate energy into tiny regions. But too much energy in too small a volume creates conditions comparable to those near black holes. The gravitational influence of the energy distorts the measurement region. This makes probing the smallest scales impossible with traditional techniques. Any attempt to examine the system closely alters the system dramatically. It's another example of the trembling effect, where the act of measurement itself disrupts the behavior the measurement is trying to capture. This trembling threshold is not chaos. It is simply the boundary between regimes we understand and regimes we cannot yet describe. Everything up to this point could be mapped with our familiar tools, even if those tools required adjustments. But past this point, meaning begins to slip. Equations stop cooperating, approximations break, frameworks become unstable. Physicists can speculate about what lies beyond, but without a unifying theory that merges quantum mechanics and gravity, those speculations remain unresolved. That uncertainty doesn't need to feel unsettling here. It can feel like an invitation to explore further, letting the unknown open gently rather than pressing for answers. There is a point in the climb toward higher and higher temperatures where the energy in a region of space becomes so dense that space can no longer remain passive. It begins responding in ways that are difficult to describe using the usual language of expansion, motion, or geometry. When temperatures are low, space appears to behave independently from whatever energy passes through it. Light travels along straight paths unless gravity curves space. Particles move and collide without altering the underlying structure of the environment. Heat may shift matter, but it does not seem to influence the shape of the space around it. That separation begins to break down once the energy density grows large. Temperature becomes so intense that space itself must participate in the process. It stretches, swells, and shifts under the burden of the energy it contains. To understand how this happens, it helps to think about how energy affects gravity. In general relativity, gravity is not a force acting at a distance, but a property of the geometry of space-time. Mass and energy shape this geometry. The more energy concentrated in a region, the stronger the curvature. When we speak of stars bending light or planets influencing each other's motion, we're talking about the effect that mass energy has on the surrounding space-time. Most of the time, the amount of energy contained in thermal motion is tiny compared to the mass of the objects involved. It does not noticeably contribute to curvature. A hot cup of tea does not bend space-time any more noticeably than a cold one. But as temperatures grow beyond everyday values, the thermal energy becomes comparable to, or even larger than the rest mass of the particles. At that point, the contribution of heat to gravity is no longer negligible. As the temperature rises, each particle carries enormous amounts of energy. This energy interacts gravitationally, adding to the curvature of space. When the energy density becomes extremely high, the curvature becomes significant enough that space-time cannot stay flat or gently curved. It responds by expanding. This expansion is not like the expansion of a balloon or the stretching of a rubber sheet. It is an expansion of the geometry itself, a widening of distances between points without any external force pushing them apart. Space grows because the energy inside it demands that growth. This effect becomes especially important in the context of the early universe. According to the standard cosmological model, the universe experienced a period of rapid expansion called inflation. The details of inflation are still being studied, and the exact mechanism is not fully established, but the basic idea is that a huge amount of energy stored in a field caused space itself to expand exponentially in a tiny fraction of a second. This wasn't an explosion. It wasn't matter rushing outward. It was space-time stretching under the influence of an enormous, nearly uniform energy density. Although inflation is not exactly the same as the behavior near the Planck temperature, both phenomena demonstrate the same underlying principle. When the energy in a region becomes too intense, space begins to swell. The extreme energy density pushes the geometry into a state where expansion becomes the natural response. This expansion changes the behavior of particles and fields because it alters the distances between points, the flow of time, and the nature of interactions. Heat does not simply make things move faster in this domain. It influences the structure containing those motions. Another way to see how energy can make space swell is through the stress-energy tensor, the mathematical object that describes how energy and momentum influence curvature. In general relativity, this tensor includes not only mass but pressure and energy flux. At extremely high temperatures, the pressure becomes enormous. The pressure is not like air pressure or the pressure of water in a container. It is a measure of how rapidly energy tries to move outward. High pressure contributes to space-time curvature just as mass and energy density do. When the pressure becomes extremely large, it enhances the expansion. Instead of resisting compression, as matter does at ordinary temperatures, the high energy fields create a situation where space responds by stretching faster. This behavior becomes more extreme as you approach the highest temperatures we can meaningfully describe. The energy density increases sharply with temperature because the number of available energy states for particles increases. Every time you raise the temperature, additional particles can be created from the energy. There is no limit to the number of particles that can appear. More particles mean more energy distributed throughout space. More energy means stronger curvature. Stronger curvature accelerates expansion. The feedback loop drives the swelling of space in a way that cannot be stopped simply by lowering the motion of particles. Space changing shape due to heat may sound strange because at familiar temperatures it never happens. Nothing you heat in your home expands the geometry of the room. But at extreme temperatures, ordinary intuition is not reliable. The pressures and energies involved are so much larger than anything found on Earth that trying to use familiar comparisons leads nowhere. Instead of thinking about temperature as heat, think about it as energy density. Energy density directly shapes space-time. When energy density becomes overwhelming, space-time must respond. Another way temperature influences expansion at high energies is through the equation of state for the early universe. The equation of state relates pressure to energy density. At ordinary temperatures, matter behaves differently from radiation. Matter's pressure is negligible, while radiation has pressure proportional to its energy density. At extremely high temperatures, all particles behave like radiation because they become effectively massless. When particles are massless, their pressure becomes a significant fraction of their energy density. This high pressure drives expansion faster than at lower temperatures. The behavior of space becomes dominated by the properties of this high-energy fluid. It is not matter expanding, it is space expanding due to the properties of the energy inside it. As temperature continues to rise, the expansion becomes so rapid that interactions between particles are influenced by the rate at which space grows. Normally, interactions depend on particles colliding or exchanging energy. But if space expands too quickly, particles are pulled away from each other faster than they can interact. This changes the nature of thermal equilibrium. The system never settles into a stable distribution because the distances between particles grow too quickly. Heat can no longer spread in the way it does at lower temperatures. The concept of thermal equilibrium begins to lose meaning. Instead of heat flowing to distribute energy evenly, expansion stretches the system before equilibrium can form. This interplay between expansion and energy density reveals why temperature stops behaving in simple ways. When space expands faster than interactions occur, the energy per particle can change without corresponding shifts in temperature, because temperature itself becomes tied to the expansion rate. In a rapidly expanding environment, energy can be diluted even while new energy appears from field interactions. This does not resemble anything in a familiar environment. Space expanding due to energy density is not comparable to heating a pot of water, where the container stays the same size. Here, the container space itself changes in response to the contents. One of the puzzles physicists face is describing what happens to geometry when energy density becomes so intense that the curvature approaches extreme values. Einstein's equations show that curvature grows without bound if the energy density grows without bound. But quantum mechanics suggests that fields and fluctuations prevent the curvature from becoming infinite. Instead, quantum corrections should modify the behavior of spacetime at very small scales. Unfortunately, we do not yet have a complete theory of quantum gravity that unifies these ideas. What we do know is that the geometry becomes irregular at the smallest scales. Instead of a smooth, continuous background, space-time undergoes small fluctuations driven by the intense energy. This foreshadows the quantum foam that appears near the Planck length. These fluctuations can be thought of as random shifts in the geometry, not because the universe is chaotic, but because quantum mechanics imposes uncertainty on all fields, including the metric that describes space-time. The amount of uncertainty increases with energy. At extremely high energy densities, the uncertainty becomes large enough to disrupt the usual behavior of geometry. Space no longer swells smoothly. It fluctuates while expanding. These fluctuations occur on incredibly small scales. They don't affect large-scale structure directly, but they do determine what happens near the threshold where physics begins to fail. This swelling of space can also be seen through the Friedmann equations, the mathematical relationships that govern the expansion of the universe. These equations show how the scale factor, which describes the size of the universe, changes over time depending on the energy content. When energy density is high, the scale factor increases quickly. When pressure is high, the expansion accelerates. At extremely high temperatures, both energy density and pressure are enormous, pushing the expansion rate to extreme levels. As you approach temperatures where the forces unify, the contributions of different fields to the equation of state change. Some fields may contribute negative pressure, which can cause accelerated expansion. This is similar to how inflation is believed to work. Even if the details differ, the principle remains. Energy density influences geometry. When energy density becomes overwhelming, geometry responds violently by stretching outward. Another consideration is how entropy behaves in this environment. In most systems, increasing temperature increases entropy because more states become accessible. But if space expands rapidly, the volume increases, and the entropy can spread across a larger region. This interplay between entropy and expansion shows that temperature is no longer a simple measure of internal energy. It becomes tied to the structure of space itself. The entropy of the universe grows not because the system becomes more disordered, but because space grows, allowing more room for possible states. Temperature becomes tied to this growth as much as to the energy of particles. Yet even with these complexities, the expansion remains smooth on large scales as long as the temperature stays below the Planck limit. Space stretches quickly but predictably. The trembling in the equations grows as the energy rises, but the geometry still follows the rules laid out by general relativity. It is only near the Planck scale that the swelling becomes so extreme that the underlying assumptions of smooth geometry break. At that point, distances fluctuate so violently that the usual concepts of expansion and curvature stop applying. The idea that energy can make space swell may feel strange from a human perspective, but it fits naturally into the mathematics governing space-time. Every increase in energy density shapes geometry. At lower temperatures, the effect is tiny and unnoticed. At higher temperatures, it becomes unavoidable. Thinking of space as a flexible medium that responds to energy helps make sense of why the universe expands. It wasn't that matter exploded outward. It was that energy shaped geometry into a state where expansion was inevitable. As the temperature rises into the domain where the energy of each particle becomes enormous, one of the strangest things begins to happen. Something that feels completely at odds with the way we're used to thinking about the building blocks of reality. Particles, the very entities that seem fundamental and unchanging at normal conditions, begin losing the traits that make them distinct from each other. The things that normally define them, mass, charge, interaction type, behavior under forces, start to shift. They don't disappear, but their unique properties fade or transform in ways that make the idea of a particle as a stable object less meaningful. It isn't that they blur physically, it's that the distinctions that let us classify them stop functioning. At these temperatures, particles struggle to maintain the identities we assign to them. They begin behaving as if they cannot decide what they are anymore. This shift doesn't begin at the very top of the temperature ladder. It starts earlier, when heat begins to erase the differences between different kinds of matter. In ordinary environments, electrons, quarks, photons, neutrinos, and other particles have distinct properties. These properties determine how they interact. Electrons have mass and a negative charge. quarks experience the strong force. Neutrinos have tiny masses and interact only weakly. Photons are massless and mediate electromagnetism. All of these differences allow the universe to have structure. At lower temperatures, these categories remain solid. No amount of heating in a laboratory will cause an electron to suddenly behave like a quark or a photon. But at extreme temperatures, far above what any experiment can reach, the distinctions stop being sharp. It is not that electrons turn into quarks or photons turn into neutrinos. Rather, the environment becomes so energetic that the properties that define each type of particle become less reliable. Masses change, interactions shift, and particles begin acting as if their defining characteristics are negotiable. The universe becomes a place where classification loses meaning. To see why this happens, it helps to start with particle mass. In the standard model of particle physics, mass comes from the interaction between particles and the Higgs field. The Higgs field has a non-zero value throughout space at low energies. Particles moving through it obtain mass by interacting with this field. The strength of their interaction determines how heavy they are. This mechanism works only when the Higgs field has its usual low energy configuration. If the temperature rises high enough, the Higgs field undergoes a transition. Its value drops towards zero. When that happens, the masses of particles effectively vanish. When particles become massless, the differences between them shrink. A massless electron no longer behaves like the familiar particle in everyday matter. A massless quark behaves differently as well. At very high temperatures, quarks and leptons all move at the speed of light. Since mass differences disappear, distinctions based on mass become irrelevant. The particles still have other quantum numbers, but the hierarchy of masses that normally separates them stops functioning. A particle that was once slow-moving at low temperatures now behaves like a high-speed, massless entity, indistinguishable in motion from any other. Another reason particles begin losing their identities is that the coupling strengths of forces change with energy scale. In quantum field theory, the strength of an interaction is not fixed. It depends on the energy of the system. At low energies, the strong force is extremely strong. The electromagnetic force is moderate. The weak force is weak. But as energy increases, the strengths evolve due to effects known as renormalization. This evolution means that multiple forces can converge in strength at high temperatures. If the forces become similar in magnitude, the particles interacting through them also start behaving in more similar ways. At even higher energies, the forces can merge into unified interactions. When that happens, the categories we use to distinguish particles by their force behavior lose significance. A particle that normally interacts electromagnetically and one that normally interacts through the weak force become aspects of the same underlying interaction at high temperatures. This merging process affects particle identity deeply. What makes an electron different from a neutrino at lower energies is partly their mass difference, and partly their behavior under the electroweak interaction. But at high temperatures, the electroweak symmetry is restored, making the distinctions between particles less meaningful. Their behavior becomes governed by unified interactions, not by separate forces. Electron-like excitations and neutrino-like excitations become different manifestations of fields behaving under the same high-energy conditions. They do not literally turn into each other, but the difference between them becomes less important in describing how the system functions. As temperatures rise even further, toward the regime where additional unification might occur, the differences between quarks and leptons also narrow. Some theoretical models suggest that quarks and leptons could share a common description at sufficiently high energies. If that is true, the categories we use to define matter, quarks forming atomic nuclei and leptons acting as spectators, would not apply. Instead, particles would be excitations of a single underlying field structure. At these energy scales, the labels we apply are more about how the particles behave at lower energies than about intrinsic differences. This shift towards unified behavior extends beyond the forces and masses The quantum field descriptions of particles break down at extremely high temperatures because the fields themselves become unstable. At lower energies, fields fluctuate slightly, but the fluctuations can be averaged out. At high enough temperatures, the fluctuations become so intense that the fields lose stable configurations. This instability means that particles cannot be defined as localized excitations in the same way. Their identities rely on fields having stable shapes. When the shapes deform constantly due to high-energy fluctuations, the idea of a particle becomes ambiguous. What we call a particle is an excitation of a field, but if the field does not hold a consistent state, the excitation loses clarity. This instability shows up as large fluctuations in quantum numbers. Quantities such as electric charge remain conserved globally, but local fluctuations can cause particles to appear and disappear rapidly. These creations and annihilations are allowed by quantum mechanics, especially at high energies. The number of particles is not conserved. If particle numbers shift constantly, with rapid conversions and interactions occurring faster than any stable classification can form, then particles cannot maintain their identities for long. The environment becomes an ocean of excitations that take on different forms depending on the energy of the moment. Another important factor is that at high enough temperature, the effective degrees of freedom in the system increase. The degrees of freedom represent the number of ways particles can move or interact. At lower temperatures, many potential states are inaccessible because they require too much energy. At high temperatures, these states become available. When the system gains access to new degrees of freedom, the ways particles can behave multiply. Their identities become more fluid because they can occupy more states. Instead of being confined to a few kinds of behavior, particles gain access to many. The environment becomes a dynamic mixture of states exchanging rapidly. The masses, charges, and interaction types that normally classify particles are not absolute, but emerge from the behavior of fields at low energy. At high energy, the mechanisms that create these differences stop functioning. Mass comes from the Higgs field. If the Higgs field behaves differently, mass behaves differently. Quark confinement comes from the strong force. If the strong force weakens at high temperatures, quarks are no longer confined. Particle types are defined by their interactions. If interactions unify, the particle types merge in behavior. Because of all these shifts, particles do not simply behave differently at high temperatures, they lose the features that separate them. It becomes impossible to treat electrons, photons, quarks, and neutrinos as distinct in the familiar sense. Their roles blur. The boundaries between categories loosen. Instead of thinking of them as separate building blocks, it becomes more accurate to think of them as expressions of fields influenced by temperature-dependent conditions. At low energy, the fields settle into stable configurations. At high energy, those configurations dissolve into a more unified structure. There is also another mechanism contributing to the breakdown of particle identity: symmetry restoration. Many of the differences between particles at low energies arise because certain symmetries in the underlying theory are broken. Symmetry breaking gives particles their masses and interaction properties. When temperature increases, the broken symmetries can be restored. Restoring a symmetry removes the distinctions created by the breaking. Particle types that were separate become aspects of a unified state. Their behavior begins following rules that apply to the unified symmetry instead of the broken version. When symmetries are restored, the universe behaves as if all particles share deeper connections not apparent at low energies. The separation of particles into categories is a low-energy phenomenon. High temperatures expose the underlying structure in which those separations do not exist. Particle identity is an emergent feature of low-energy physics, not a fundamental property at all temperatures. As the system moves closer to the highest temperatures imaginable, the instability grows so intense that any useful distinction between particles fades almost entirely. It becomes difficult even to define a particle because the concept relies on having identifiable excitations against a stable background. If the background shifts constantly due to quantum fluctuations, the excitations cannot be defined in a fixed way. They overlap, transform, and lose the coherence needed for classification. At the threshold where quantum gravity becomes important, even the notion of space and time needed to define particle trajectories begins to slip. This is not to say that particles become meaningless. They still exist as excitations of fields. But those excitations become so short-lived and so heavily influenced by the surrounding conditions that describing them with the usual labels becomes impractical. It is like trying to identify individual waves in a stormy ocean when the water is rising, falling, crashing, and splashing too rapidly to follow. The waves exist, but none of them maintains a shape long enough to categorize or track. Another way to understand this loss of identity is to consider that particle interactions become so frequent and energetic that any distinction becomes temporary. A particle might behave like one type for a moment, then shift to a different state due to an interaction, then return or transform again. The transitions become fast enough that the idea of a stable type is replaced by a fluid set of possibilities. The system becomes dominated by transformations rather than by stable forms. As the temperature rises even further, approaching the range where our theories begin to fail entirely, the distinctions that define particles at low energies continue dissolving. Instead of a collection of separate particles interacting through distinct forces, the universe resembles a unified medium where excitations occur with no clear boundaries. The idea of particle identity, which works so well at low energies, becomes a simplified version of the truth, a truth that reveals itself only in the extreme conditions near the peak of possible temperatures, where the deeper structure of reality begins to appear. As the temperature keeps rising and the behavior of particles becomes more and more fluid, an even deeper shift begins to unfold, one that affects not just the particles themselves, but the structure of interactions that govern their behavior. At low energies, the universe operates with four distinct fundamental forces. Gravity shapes the motion of stars and planets. Electromagnetism controls the behavior of charged particles, light, and chemistry. The strong nuclear force binds quarks inside protons and neutrons. The weak nuclear force governs certain forms of decay. These forces seem separate and unrelated in daily life, each with its own range, its own strength, and its own rules. But those differences are not permanent features of nature. They emerge only at low energies. When the temperature climbs into the realm where the identities of particles blur, the differences between these forces begin to dissolve as well. Understanding why this happens requires looking at how forces work in modern physics. Each force is described not by a physical push or pull, but by fields that fill all of space. Particles interact by exchanging excitations of those fields, often called force carriers. Photons carry the electromagnetic force. Gluons mediate interactions between quarks through the strong force. W and Z bosons govern the weak force. Gravitons, though not yet observed, would carry gravity if gravity can be described as a quantum field. These particles have different masses, different charges, and different interaction patterns. Their distinctions create the separate behavior of forces at ordinary temperatures. But as we move toward higher temperatures, the distinctions between force carriers begin to weaken. For example, at temperatures far above anything we can reproduce in a laboratory, the electromagnetic and weak forces merge into a single electro-weak interaction. This is not speculation. It is supported by both theory and experimental evidence. At room temperature, the photon is massless, while the W and Z bosons are massive. That mass difference makes the weak force short range and the electromagnetic force long range. But at extremely high temperatures, the Higgs field loses the configuration that gives W and Z their mass. Once the masses vanish, the weak force becomes long range, just like electromagnetism, and the symmetry between the fields is restored. Instead of two forces, there is only one. Electroweak unification is one of the clearest examples of how heat can erase distinctions that appear fundamental at low energies. If the temperature rises even further, beyond electroweak unification, theories suggest that additional unifications can occur. The strong force, which usually behaves very differently from electromagnetism, and the weak force may merge with them under certain high-energy conditions. This possibility depends on the details of grand unified theories, or GUTS. While no single model has been confirmed, many of them predict that at sufficiently high temperatures, the strong force's unique behavior fades. Instead of quarks being confined within protons and neutrons, as they are at low energies, they would move freely in a state where the distinctions between quarks and leptons are narrower. In this environment, the fields governing the strong interaction and the electro-weak interaction could be different expressions of one broader force. One of the things that drives this blending is the way the strengths of forces change with energy. At low temperatures, the strong force is much stronger than electromagnetism. But as energy rises, its strength gradually decreases, while the strength of the electro-weak interaction slowly increases. At some extreme energy scale, their strengths can match. When that happens, the mathematical descriptions of the forces can fit into a single unified framework. The forces do not merge in a physical sense the way liquids might blend. Instead, the equations describing them undergo symmetry restoration, revealing that the forces were parts of a larger symmetric structure at high energies. This process reflects a deeper principle. Distinctions between forces arise because the underlying symmetry of the universe is broken at low energies. As the universe cools, fields settle into specific configurations that break the symmetry and create differences between interactions. When the universe was hotter, those symmetries were intact. Melting that symmetry with heat restores the earlier state where the forces are unified. The idea of symmetry breaking can feel abstract, but its effects are straightforward. At refrigerator-side temperatures, water freezes into ice, forming crystal structures that break the symmetry of liquid water. If you melt the ice, the symmetry returns. Something similar happens with the forces. At low energies, the fields settle into specific patterns and break large symmetries into smaller ones. At high energies, temperature melts the broken patterns and restores larger symmetries. The result is a simpler, more unified interaction. When the temperature grows even further, some theories predict that the electroweak and strong forces merge with gravity. This final unification would require reaching energies near the Planck scale. At that point, gravity would no longer be the weak, large-scale force we observe. It would become comparable in strength to the other forces. This shift is one of the motivations for seeking a theory of quantum gravity, something that could describe gravity in the same language as the other forces. Without such a theory, we cannot explain exactly how the unification would take place. We only know that at temperatures approaching the Planck energy, the separation between gravity and the other forces likely dissolves. Even without a complete theory, we can still understand why gravity would merge with the other forces at high energies. Gravity's strength depends on the energy scale. At low energies, gravity is extremely weak compared to the other forces. But as energy rises, gravity becomes stronger. Meanwhile, the other forces either weaken or change their behavior. Eventually, all forces may meet at a common strength, where they can be described within a single mathematical structure. When we talk about the blurring of forces, we're not saying the forces literally become identical in every sense. Instead, we're saying that the mathematical descriptions of the forces merge. What looks like separate behaviors at low energies are different manifestations of the same system. The universe hides its higher order symmetry under low energy conditions. Heat removes that concealment. Instead of the universe showing us only its low energy face, it begins revealing the deeper simplicity beneath. The blending of forces also affects particles. A particle's identity is tied to the forces it interacts with. Electrons interact electromagnetically. Neutrinos interact weakly. Quarks interact strongly. But if the forces unify, the interactions lose their characteristic differences. A particle interacting through the electroweak force begins to behave in a way that is not easily distinguished from a particle interacting through the strong force if everything has merged into one interaction at high energies. The merging forces allow particles to behave as if they share a common foundation. The categories separating them shrink because the forces defining them shrink. Temperature plays a key role in revealing how this unification unfolds. The behavior of forces at high temperatures is governed by quantum field theory and renormalization group equations. These equations describe how the properties of particles and interactions shift with energy. As energy rises, the parameters of the fields evolve, gradually aligning. When the parameters become equal, the forces unify. This unification changes the way fields behave and how particles move. Particle decay processes also change at these temperatures. At lower energies, particles decay in specific ways because the forces governing the decays are distinct. For example, a neutron decays through the weak force, but at high temperatures, decay channels can change because the distinction between forces fades. A particle may undergo transitions that are forbidden at low energies. The classification of decays and interactions becomes more flexible because the forces governing them have merged. Another aspect of this merging is that the effective degrees of freedom increase. Ordinarily, particles have different masses and charges that restrict their interactions. When forces unify, the restrictions decrease. Particles gain access to more possible interactions. They can transform more easily, move more freely, and distribute energy more uniformly. The system becomes more symmetric, meaning the rules governing its behavior apply more uniformly across particle types. At extremely high temperatures, the vacuum state of the universe also changes. At lower energies, the vacuum has a structure shaped by broken symmetries. This structure determines particle masses and the appearance of forces. At high energies, the vacuum loses its low-energy configuration. The fields flatten out. Symmetry is restored. Without symmetry breaking, the masses vanish and the fields behave more uniformly. This means the forces behave uniformly as well. The merging of forces is deeply connected to the configuration of the vacuum. This shift reveals something important. Particles and forces are not fundamental in the everyday sense. They are low-energy expressions of deeper fields shaped by symmetry and its breaking. At high temperatures, the low-energy structure melts, showing that the distinctions were never fundamental. They were temporary features arising from the universe cooling down. As temperature rises toward the unification scale, the merging of forces becomes increasingly complete. The equations describing the interactions become simpler despite the environment being more extreme. What looked like 4 separate interactions becomes one. What looked like different carriers become aspects of a unified field. The universe begins to resemble its early state, before cooling fractured the symmetry and produced the variety of forces we see now. Near the temperatures where more unification is expected, the system grows increasingly unstable because quantum fluctuations become enormous. These fluctuations affect the fields that mediate the forces. They distort the background geometry and influence the structure of the vacuum. The merging of forces becomes tied to the merging of space-time behavior with field behavior. No part of physics stays separate. Everything becomes interconnected. Eventually, at even higher temperatures, the theories describing unification run into the limits of quantum field theory. Without a theory of quantum gravity, we cannot follow the merging all the way to the Planck scale. What we do know is that before reaching that scale, the distinctions between forces that govern our world, gravity bending space-time, electromagnetism shaping atoms, the strong force binding quarks, and the weak force enabling decay, are all expected to blur. They become different aspects of one deeper interaction that is only visible near the highest temperatures the universe can support. When we trace the story of the universe all the way back through every stage we've explored so far, the temperature keeps rising until we reach conditions so extreme that the descriptions we use today begin to lose structure. But before the temperature climbs to the very top, before it reaches the point where all the laws we know fall apart completely, there is a period that sits just beyond the reach of our experiments, yet remains close enough that our theories can still offer a guided picture. This period is often described as the moment the universe took its first breath, although that is not a literal description. There was no air, no lungs, no pause between inhaling and exhaling. It was simply the earliest interval in which the universe existed as something with physical properties, something with energy, something with fields that behaved in ways we can still trace through the mathematics of cosmology. This moment, if one tries to imagine it gently, was when space-time itself began unfolding into a form we can eventually recognize. The earliest fraction of a second after the beginning is so short that human intuition does not grasp it naturally. Even calling it a moment is misleading because the duration is so tiny that the word moment carries more weight than the interval deserves. Yet it was long enough for the universe to undergo transformations that still influence everything around us today. During this interval, energy densities were enormous. Temperatures were far above anything possible in nature now. Particles were so energetic that they could not hold on to stable identities. Forces merged. Space expanded. Quantum fluctuations shaped the large-scale structure we see billions of years later. Trying to visualize it directly is nearly impossible because everything we rely on for visualization, familiar objects, familiar motion, familiar distances, did not exist then. Instead, what we have are mathematical descriptions and clues left behind in the distribution of matter throughout the cosmos. To ease into this earliest period, it helps to recall that time, in our usual sense, did not function the way it does now. Today, time progresses at a steady rate, measured by the rhythm of clocks, the vibration of atoms, or the motion of celestial bodies. But in the earliest stages of the universe, time was deeply connected to the expansion rate, which was changing rapidly. It moved differently from what we're used to. When we speak of the universe's first breath, we're describing a stretch of time so short that even the smallest intervals we measure today feel vast in comparison. The Planck time, the shortest meaningful duration in modern physics, is roughly 5.3910^44 seconds. The earliest universe evolved through changes happening over scales comparable to that. Entire transformations occurred faster than any process we can observe now. At temperatures this high, the universe was filled with a dense, hot mixture of fields and particles. But even calling them particles is somewhat misleading. The distinctions we normally use to categorize particles do not apply. Instead, everything behaved as a unified fluid of energy. This fluid did not sit still. It was expanding. The expansion was not gentle. It was rapid, driven by the enormous energy density that filled space. Modern cosmology describes this stage with equations that relate the expansion rate to energy content. The hotter the universe, the faster it expanded. In this earlier stage, the temperature was so high that the expansion was extraordinarily rapid. This expansion was not like a burst from a central point. It did not have a center at all. It wasn't an explosion. It was space itself stretching everywhere at once. Points in space that were once close became farther apart. Distances grew. There was no outside into which this expansion occurred. The universe expanded from within itself because space-time is not embedded in anything else. Its own geometry sets the rules. This distinction is important because imagining an explosion tends to conjure images of debris rushing outward into empty surroundings. Nothing like that happened. There was no empty space to expand into. There was only the universe itself, growing from a state of unimaginably high energy density. During this early stage, the contents of the universe were dominated by radiation. Matter, in the everyday sense, did not exist. Atoms could not form because the temperature was far too high for electrons to bind to nuclei. Even the nuclei themselves had not yet formed. Quarks moved freely in a dense plasma. Gluons, which at lower energies confine quarks into particles like protons and neutrons. behaved differently under these extreme conditions. The confinement broke down. Quarks and gluons spread through the universe like a fluid. Electrons, neutrinos, and other leptons also moved freely. The photons present were so energetic that they constantly produced new particle-antiparticle pairs. Nothing stayed the same for long. The interactions were rapid and violent, yet they were governed by underlying laws that kept the environment evolving smoothly in a large-scale sense, even if the microscopic behavior was turbulent. One of the most important features of this earlier stage was the presence of quantum fluctuations. Quantum mechanics allows fluctuations in energy and fields even in the vacuum. These fluctuations are normally tiny, smoothing out when averaged over large regions. But during the first breath of the universe, the expansion stretched these fluctuations. Small variations in density grew larger as the universe expanded. Over time, these variations became the seeds of galaxies, clusters, and the large-scale structure we observe today. It might seem strange that random fluctuations could shape cosmic architecture, but the mathematics of inflation and quantum field behavior show how small irregularities become amplified by rapid expansion. The earliest breath of the universe not only contained intense temperature and energy, but also the beginnings of structure that would grow over billions of years. Another key aspect of this period is that interactions between particles happened constantly. Collisions occurred so frequently that the system maintained thermal equilibrium despite the extreme conditions. Temperature was well defined because energy flowed rapidly enough to keep everything mixed evenly. This equilibrium meant that the universe behaved like a uniform radiation bath. But as the expansion continued, reaching into larger and larger scales, maintaining equilibrium became more challenging. Eventually, certain interactions could no longer occur fast enough to keep up with the expansion. At that point, the system began transitioning out of equilibrium, leading to important changes that shaped later evolution. Before equilibrium started to break down, though, the universe was simple in some ways. It was a single fluid of high energy fields with no stable structures. The differences between particles were minimal. The differences between forces were shrinking. Space was expanding rapidly, and temperature was decreasing as a result of that expansion. When the universe expands, radiation cools. The energy per particle becomes lower because the wavelength of each photon stretches with the expansion. This stretching creates a cooling effect that eventually drops the temperature below the threshold, where certain processes can occur. As the universe cooled, certain symmetries began to break. Symmetry breaking is one of the central events that shaped everything that followed. At high temperatures, the forces were unified. As the universe cooled, the unified interactions split into separate forces. The electro-weak force separated into the electromagnetic and weak forces. Later, the strong force crystallized into its familiar behavior. These symmetry breakings were not gentle transitions. They were phase transitions, somewhat like water freezing into ice. When symmetry breaks, the fields involved shift into new configurations. These shifts influence the properties of particles, giving them mass and defining their interactions. Every particle that exists today owes its identity to these transitions. Without them, the universe would be unrecognizable. Another insight into this early period comes from considering how matter and antimatter behaved. For reasons not fully understood, the universe ended up with more matter than antimatter. The earliest conditions would have allowed matter and antimatter to form in equal quantities. But due to a small imbalance in their interactions, matter eventually dominated. During the universe's first breath, matter and antimatter were created and destroyed constantly. The temperature was high enough for photons to convert into pairs of particles and antiparticles repeatedly. But as the universe expanded and cooled, many of these pairs annihilated, producing photons. Only the small excess of matter remained. This tiny imbalance made the existence of stars, planets, and everything else possible. Without it, matter would have vanished in a sea of energy. Not all transitions that occurred in this early stage are fully understood. Some are based on solid evidence supported by particle physics and cosmology. Others remain theoretical. But together, they form a picture that allows us to describe the universe's earliest behavior with surprising confidence, considering how far removed these conditions are from anything we can directly observe. The temperature during this first breath can be traced using the known expansion history of the universe. As we work backward, the temperature rises steadily. At around a microsecond after the beginning, the temperature was high enough for quarks and gluons to remain unconfined. At around a trillionth of a second, the electroweak symmetry was restored. At even earlier times, we approached the temperatures where grand unified theories might apply. All these stages occurred within an unimaginably brief interval. The universe transitioned through them as it expanded rapidly, each step lowering the temperature and revealing new layers of structure. Despite the extreme conditions, the universe was remarkably smooth at large scales during this early stage. That smoothness is evident in the cosmic microwave background radiation, which preserves temperature variations from roughly 380,000 years later. Those variations are incredibly small, only 1 part in 100,000. This smoothness tells us that the earliest universe was nearly uniform. That uniformity required interactions to happen quickly enough to distribute energy evenly. It also required a period of rapid expansion that smoothed out irregularities. That early expansion phase, inflation, played a role in preparing the universe for the later stages of structure formation. As we examine the earliest breath through modern theoretical tools, we find that some features are surprisingly stable. The expansion rate, the energy density, and the temperature all follow predictable patterns described by the Friedmann equations. Even though the microscopic behavior was chaotic, the large-scale behavior was stable enough for cosmologists to trace backward using the laws of physics we know. That stability is one reason we can study these early conditions with confidence. Yet even with that stability, the earlier stage still challenges our understanding. The temperature becomes so high that quantum fluctuations dominate. The energy density becomes so large that gravity behaves in ways we cannot fully describe. Particles lose their identities, forces merge, space expands rapidly, fields shift into new configurations. These transformations are at the heart of the universe's earliest behavior. While the earliest breath did not last long, it shaped everything that came after it. The seeds of galaxies formed. The distribution of matter was set. The forces separated. The masses of particles emerged. The imprint of this early stage remains visible today in the large-scale structure of the universe and in the faint glow of the cosmic microwave background. Up to this point, we've been moving through regimes where particles lose their identities, forces begin to merge, and energy density becomes so large that space itself expands in response. Each step toward the upper limit has made the behavior of matter and fields less familiar, but the geometry of space has still been something we can picture in broad strokes. Even when expansion accelerated, space remained smooth enough that we could describe it with equations from general relativity. But as we push closer to the most extreme temperatures, that smoothness dissolves. The calm fabric of space-time that seems so steady at ordinary scales begins shifting, flickering, and fluctuating in ways that no longer resemble the continuous geometry we use in almost every area of physics. At this point, what dominates is something often described as quantum foam. Not foam in any visual sense, but a state where the geometry of space-time changes so rapidly and on such tiny scales that our usual concept of distance stops being meaningful. To understand why this happens, it helps to revisit the way quantum mechanics describes the world. In quantum mechanics, every field has fluctuations. Even in empty space, fields fluctuate slightly. These fluctuations arise from the uncertainty principle, which does not allow energy or position to be perfectly fixed. At large scales, these fluctuations average out. Space appears smooth and stable. But as you probe smaller scales, the fluctuations become more pronounced. At scales near the Planck length, they become so significant that they shape the behavior of space-time itself. Instead of being a gentle background, space becomes a dynamic environment filled with constant changes. These changes are not due to particles moving around. They are intrinsic to the geometry itself. General relativity assumes that space-time is smooth. It can be curved, bent, or stretched, but it is always continuous. This assumption works well when the energy involved is not too large. But when the temperature rises toward the extreme limit, where the energy density becomes overwhelming, quantum fluctuations become strong enough to disrupt the continuity assumed by general relativity. We cannot have a smooth metric describing distances because the underlying fields fluctuate too violently. These fluctuations cause tiny warps, dips, rises, and distortions in the geometry that appear and vanish in incredibly short intervals. The result is a space-time that behaves more like a constantly shifting surface than a smooth field. Another way to think about this shift is through the concept of measurement. Measuring distance or time requires using probes, whether those probes are photons, particles, or more theoretical constructs. But as we approach extremely high temperatures, the energy required to probe small scales produces strong gravitational effects. Trying to measure a distance shorter than the Planck length, for example, would require so much energy in such a small region that it would create a curvature strong enough to form a microscopic black hole. This makes precise measurements impossible. The act of probing small scales distorts the region being measured. This limitation is not simply a technological barrier, it is a fundamental limit imposed by the combination of quantum mechanics and gravity. These measurement limitations reflect the deeper issue that distances do not exist in the usual sense at these scales. When space-time fluctuates so rapidly, a straight line cannot be defined consistently. A point cannot be fixed. Two events cannot be precisely separated. The entire framework of geometry loses meaning because the background it relies on no longer behaves predictably. Instead of smooth distances and times, we get a seething environment where the geometry changes too quickly to form a stable structure. As the temperature approaches this extreme regime, the energy density increases beyond anything describable by particle physics alone. Quantum field theory assumes a fixed background space in which fields operate, but at these temperatures the background cannot be treated as fixed. The energy of the fields themselves curves the background. The curvature then influences the fields, which change the curvature again. This feedback loop becomes so intense that it cannot be captured by our current theories. Quantum mechanics alone cannot handle space-time curvature. General relativity cannot handle quantum fluctuations. When both effects are overwhelming, neither theory applies cleanly. Quantum foam emerges in this environment because fluctuations in energy at tiny scales produce curvatures comparable to the scale of the fluctuations themselves. The geometry bends, twists, fluctuates, and returns to a different configuration repeatedly. These changes happen in intervals far shorter than any process we can observe today. They happen so quickly that trying to trace them with familiar tools would require measuring intervals shorter than the Planck time, which is impossible with current or imaginable technology. The foam is not something we would be able to see, even if we were immersed in it. It is a theoretical description of what happens when quantum uncertainty affects the geometry itself. This foam-like behavior can be thought of as a limit where the distinction between fields and geometry begins to blur. At lower temperatures, fields, particles, and forces operate within space-time. The geometry of space-time determines how they move. But at extremely high temperatures, fields and geometry interact so strongly that they can no longer be separated. Fluctuations in fields become fluctuations in space-time. Fluctuations in space-time become fluctuations in fields. The universe becomes a single, interconnected system where geometry and matter cannot be described independently. Some approaches to quantum gravity try to capture this behavior. They attempt to describe space-time as something with a granular structure at extremely small scales. However, not all approaches agree on what this structure looks like. Some theories describe space-time as a network of interconnected loops. Others describe it as a discrete set of building blocks. Others treat it as emerging from deeper quantum structures. But they all agree that at scales near the Planck length, the smooth geometry of general relativity breaks down. Space-time must be described by something that includes quantum fluctuations from the start. The foam also influences how energy behaves at these scales. In ordinary conditions, energy flows through fields in predictable ways. But when space-time fluctuates, the pathways of energy become unstable. The curvature changes the paths of particles. Particles appear and vanish rapidly. Disturbances propagate through the foam unpredictably. The speed at which disturbances travel may vary slightly due to the geometry shifting. Even the idea of a straight path becomes meaningless, because the space through which something moves changes shape as it moves. This instability challenges the very concept of temperature as well. Temperature normally describes how energy distributes among particles, but if particles cannot be defined clearly, and the geometry they occupy fluctuates too rapidly for equilibrium to form, temperature becomes a rough indicator rather than a precise measure. It becomes an energy scale describing how intense the fluctuations are rather than something that can be tied to well-defined particle behavior. As the foam intensifies, the biggest obstacle becomes the inability to define a stable vacuum. At ordinary energies, the vacuum is not empty. It contains fluctuations, but they are small. At high energies, the vacuum becomes unstable. The fluctuations are enormous. New configurations form constantly. Fields shift repeatedly. The vacuum becomes an environment filled with rapidly changing structures that influence every particle trying to move through it. This instability is expected to dominate near the Planck temperature. At that point, the foam becomes so intense that even the equations used to describe the fluctuations lose meaning. The framework needed to describe such conditions must include elements of both quantum theory and gravity. Without that unified framework, physicists can only speculate about what the foam truly looks like, or how it behaves. Even without a complete theory, we can infer some characteristics of the foam from the limitations of existing theories. For example, if the foam creates fluctuations in space-time curvature, then the geometry may be constantly producing regions of slightly higher or lower curvature. In some areas, space might pinch inward. In others, it might stretch outward. These changes would not persist long enough to form black holes or stable geometric structures. They would appear and vanish quickly. The environment would be constantly shifting, dominated by transitions too rapid to observe. Another implication is that causality becomes, at least temporarily, harder to define. At ordinary scales, cause and effect follow from the structure of space-time. Events separated by certain distances cannot influence each other instantly because signals travel at finite speeds. But in a foamy environment where the geometry fluctuates, the separation between events becomes uncertain. Distances change. The timing of events becomes fuzzy. This does not violate fundamental physical principles, but it does mean that our familiar descriptions of cause and effect cannot apply in the same way. This environment can also influence what is possible for energy levels. In quantum field theory, some processes are forbidden because they violate energy conservation or other constraints. But in the foam, fluctuations can temporarily create conditions where forbidden processes become possible for extremely short times. These processes do not persist long enough to violate larger-scale conservation laws, but they do show how different the environment becomes. The foam allows transitions that defy ordinary expectations, though they occur only at scales where the foam dominates. The unpredictability of the foam suggests that the behavior of particles becomes dominated by intense fluctuations rather than stable patterns. Instead of moving along well-defined paths, particles may undergo rapid changes in direction. They may switch between states. Their energies may fluctuate unpredictably. The foam imposes a level of uncertainty that is far greater than anything encountered at lower energies. Another interesting aspect of this environment is that the foam might blur the distinction between space and time. In general relativity, time is part of the same structure as space, but the symmetries of space-time hold only when the geometry behaves smoothly. When the geometry fluctuates, the distinction between space and time may become ambiguous. Tiny regions might behave as if time and space switch roles. This does not affect the large-scale passage of time, but it does influence how processes unfold at extremely small scales. The presence of foam also raises questions about the nature of singularities. In classical general relativity, singularities occur where curvature becomes infinite. But if quantum fluctuations dominate at small scales, they may prevent true singularities from forming. The foam might spread out the effects of extreme curvature, preventing the geometry from collapsing into a single point. This possibility is one reason some physicists believe that quantum gravity will remove singularities from our understanding of space-time. The foam could act as a natural regulator, preventing geometry from becoming too extreme. As the temperature rises further, the foam's behavior becomes increasingly difficult to describe without a unified theory. The fluctuations grow stronger, the geometry loses more stability, fields behave more chaotically. The separation between particle behavior and geometric behavior becomes meaningless. Everything merges into a single, rapidly fluctuating system dominated by energy and uncertainty. The environment becomes even more extreme. The foam intensifies, the geometry becomes even more unstable, and the behavior of energy becomes even harder to track. Yet each step brings us closer to understanding the domain where the familiar laws of physics give way to something new, something we do not yet have the tools to describe fully, but can approach gently by following the clues that arise from all the regimes leading up to this point. As we move deeper into the landscape of extreme temperatures, the behavior of gravity begins to shift in a way that feels completely different from how we experience it in the world around us. At ordinary conditions, gravity seems steady, predictable, and firmly tied to mass. You feel its pull every time you take a step, lift an object, or watch something fall. Planets move in their orbits because gravity holds them in place. Stars form because gravity pulls gas together. Even at cosmic scales, gravity is the glue shaping galaxies and clusters. Yet when the temperature climbs far enough, pushing the universe into realms where energy dominates everything else, gravity stops behaving with the familiar strength and steadiness we see today. Instead, it gradually loses its tight grip. The overwhelming heat disrupts the conditions that make gravity behave as it does now. The higher the temperature rises, the more gravity's influence softens relative to the other forces. Eventually, at truly extreme levels, gravity's distinct identity begins to fade. This weakening does not mean gravity disappears. It does not suddenly switch off. Rather, its relative importance diminishes because the energy present at extreme temperatures no longer behaves in ways that allow gravity to dominate. To understand why this happens, it helps to recall how gravity fits into the framework of modern physics. In Einstein's general relativity, gravity is not a force transmitted by a particle, in the same way electromagnetism is transmitted by photons. Instead, gravity is the curvature of space-time caused by mass and energy. The more mass or energy in a region, the more space-time curves. At everyday scales, mass dominates energy. In planets, stars, and galaxies, most of the energy present comes from matter's rest mass. Because of that, gravity is largely shaped by mass. At high temperatures, however, the contributions of mass and energy shift dramatically. As the temperature rises, particles move faster. Their kinetic energy increases. When particles gain enough energy, that energy becomes comparable to, or greater than, their rest mass. In this regime, mass is no longer the overwhelmingly dominant contributor to gravity. Instead, kinetic energy becomes equally important. This shift means gravity becomes more sensitive to the types of energy present. But more importantly, it means the distinctions that normally make gravity weak relative to the other forces begin to break down. What makes gravity seem weak at low energies is that mass is a slow-moving property. It doesn't change quickly. Electromagnetic interactions, by contrast, can be incredibly strong because charges move and respond rapidly. The strong force is even more intense at low energies, binding quarks with enormous strength. But as energy increases, the strengths of the other forces change. The strong force becomes weaker at high energies, losing the extreme strength it shows at low energies. The electromagnetic and weak forces become more similar in strength at high energies, eventually merging. In this shifting landscape, gravity begins to behave differently as well. Even though gravity's underlying description remains tied to space-time curvature, the relative importance of curvature compared to field interactions changes. Another way to understand the weakening of gravity's grip is to consider how energy density interacts with geometry. At extremely high temperatures, energy density becomes enormous. This energy density contributes to the curvature of space-time. But because the temperature also increases the pressure of the energetic mixture, and pressure itself contributes to gravitational effects, the overall gravitational influence of the environment becomes tied to these extreme pressures. Yet at the same time, the enormous energy density also accelerates the expansion of space. When space expands rapidly, the gravitational pull between regions weakens. Points move apart faster than the gravitational attraction can act between them. This behavior appears in the early universe, where the expansion outpaced gravitational collapse. Even in the presence of immense energy, the expansion was so strong that gravity could not pull things together in the way it does today. This relationship between expansion and gravity becomes even more complex at ultra-high temperatures. The rapid expansion effectively dilutes the effect of gravity. Instead of pulling matter together, gravity is overwhelmed by the stretching of space. In this environment, even regions with high energy density cannot collapse because the expansion outruns the ability of gravity to act. This is one of the reasons the universe did not collapse back into itself immediately after its earliest phases. The temperature was so high and the expansion so rapid that gravity had little opportunity to assert its usual influence. The weakening grip of gravity also relates to how masses behave at high temperatures. At lower temperatures, particles have stable masses determined by their interaction with the Higgs field. These masses give gravity something concrete to act on, but when the temperature becomes high enough to alter the Higgs field, particles lose their masses. Without mass, gravity's effect becomes tied solely to energy. Massless particles still curve space-time, but they do so differently. The disappearance of stable masses removes one of the primary sources of gravity's familiar influence. This change does not eliminate gravity, but it alters the way gravity interacts with the energetic mixture. Without mass differences, the contributions of particles to gravity become more uniform. The distinctions that normally shape how matter collapses under gravity vanish. Gravity becomes tied solely to the total energy density, not to the differences between particle types. This uniformity reduces the role of gravity in shaping structure, because no stable structure can form at these temperatures. Everything behaves like a single fluid, with no density contrast large enough for gravity to amplify into structure. In effect, gravity becomes a spectator to the environment rather than a dominant force. Another reason gravity's influence fades at high temperatures is related to how the other forces behave. At ordinary energies, the strong and electromagnetic forces dwarf gravity. Even the weak force, though weaker than electromagnetism, is much stronger than gravity at the scale of particles. As the temperature increases, the strengths of these forces evolve. The strong force grows weaker due to asymptotic freedom. The electromagnetic and weak forces merge and become stronger in relation to the strong force. In this environment, gravity's relative weakness becomes even more pronounced. If all the forces approach similar strengths at high energies, gravity remains the weakest. It does not catch up. Instead, it becomes a minor component of the interaction landscape. This shift has profound consequences for how the universe behaves at these temperatures. Gravity cannot stop the rapid expansion. It cannot form stable structures. Particles do not settle into configurations where gravity dominates. Instead, the universe becomes dominated by interactions among fields and by the behavior of space-time under intense energy densities. The usual balance between expansion and gravitational attraction does not apply. The expansion wins easily, and gravity remains unable to impose order on the environment. These effects become even more pronounced as we approach temperatures near the point where all forces may unify. At those scales, theories suggest that gravity's behavior could begin to resemble the behavior of the other forces. In grand unified theories, the strong and electro-weak forces merge, but in some speculative models, gravity might also merge with them at even higher energies. This would mean gravity no longer stands apart. It would be one component of a single interaction. In such a scenario, gravity's apparent weakness at low energies is simply a feature of symmetry breaking at lower temperatures. At high temperatures, gravity could have behaved in a way that is impossible to describe using our current low-energy understanding. However, this merging has not been demonstrated experimentally or even fully supported theoretically in a single consistent model. It is part of the reason physicists seek a theory of quantum gravity. Without such a theory, we cannot follow gravity's behavior all the way to the highest temperatures. What we do know is that before reaching any hypothetical unification point, gravity begins to lose its familiar form. The gravitational influence of mass fades as masses vanish. The gravitational influence of energy competes with rapid expansion and loses. The geometry begins fluctuating due to quantum effects. Gravity becomes more a property of an unstable environment than a guiding force shaping behavior. This environment, where gravity's influence weakens, helps explain why the early universe was so smooth. At lower temperatures, gravity amplifies density differences. Slightly denser regions pull more strongly, becoming denser still. This process eventually forms galaxies and clusters, but at very high temperatures, gravity could not amplify these differences because expansion stretched regions apart too rapidly. Even if one region had slightly more energy than another, gravity did not have time to act before expansion diluted the difference. The result was a nearly uniform universe, with only tiny fluctuations that later grew under gravity once the temperature cooled enough for gravity to regain influence. Another reason gravity loses strength relative to the environment is that energy densities approach levels where quantum fluctuations in space-time cannot be ignored. Instead of gravity producing gentle curvature, the fluctuations produce irregular and unpredictable distortions. Gravity's role becomes uncertain because the background space-time no longer behaves smoothly. General relativity relies on smooth geometry to describe gravitational effects. If the geometry fluctuates, the predictions of general relativity cannot be trusted. In such an environment, gravity becomes a concept that needs quantum treatment. But without a quantum theory of gravity, the behavior remains unclear. At these temperatures, even the idea of a gravitational field becomes unstable. In normal conditions, the gravitational field is described by the curvature of space-time. The curvature remains smooth enough that we can draw lines and describe how test particles move. But if the curvature fluctuates on tiny scales, the gravitational field cannot be defined consistently. In some regions, curvature might increase due to a fluctuation. In others, it might decrease. The geometry shifts constantly in response to both quantum fluctuations and the enormous energy density. Gravity becomes entwined with the foam-like behavior of space-time itself, losing its identity as a predictable, steady influence. This gradual fading of gravity's grip also explains why the earliest universe did not collapse into a black hole. At lower energies, if you compress enough mass into a small enough region, gravity becomes strong enough to form a black hole. But the early universe had enormous energy density concentrated into a tiny region. Shouldn't that have formed a black hole? The answer lies in expansion. The expansion was so rapid that no region remained within the gravitational radius needed to collapse. For a black hole to form, the collapse must overcome expansion. In the early universe, expansion always won. Heat weakened gravity's role by driving geometry outward faster than gravity could act inward. As the temperature rises further, approaching the point where quantum foam dominates, gravity becomes increasingly inseparable from the geometry's unpredictable fluctuations. Its effect can no longer be treated as an orderly curvature. Instead, gravity becomes a property of a chaotic environment. The massless high-energy particles contribute to curvature, but the curvature does not behave predictably. Energy and curvature bounce off each other in rapid transitions. Gravity becomes one element of a rapidly shifting system rather than a guiding steady force. As the temperature rises into ranges where gravity weakens and quantum fluctuations begin shaping the environment more than any familiar force, the question naturally appears in the mind. If these conditions are so important for understanding the universe, why not recreate them? Why not build a machine powerful enough to reach these temperatures, even briefly, so we can observe directly what happens? The idea feels simple at first, especially considering the progress physics has made by pushing farther into high-energy domains. Particle accelerators have allowed us to probe smaller and smaller scales. Technologies have advanced dramatically. But when discussing the temperatures involved in the extreme upper limit of physics, the situation becomes fundamentally different. No experiment, no machine, no clever design could ever create conditions close to these temperatures. It isn't just a matter of engineering difficulty. The limitations arise from the laws of physics themselves. They prevent any attempt to reach these extremes from succeeding, no matter how far technology advances. Understanding this requires starting with the scale of temperature involved. The Planck temperature is roughly 1.416 10^32 Kelvin. That number is so large that comparing it to everyday temperatures becomes meaningless. Even the hottest fusion reactions inside stars reach around 108 Kelvin. The conditions inside supernovae reach around 1010 Kelvin. The early universe, microseconds after the beginning, reached around 1015 Kelvin. Modern particle accelerators can reach effective temperatures corresponding to energies around 1012 Kelvin during collisions. These numbers are vast, yet they remain tiny compared to the Planck temperature. Even if you scale up particle accelerators by enormous factors, the difference remains overwhelming. A quadrillion-fold increase still would not be enough. The temperatures we're discussing sit so far beyond what any experiment can achieve that even imagining a machine capable of generating them becomes unrealistic. One of the core limitations is energy concentration. Temperature in particle physics corresponds to the average energy per particle. To reach higher temperatures, you must compress immense amounts of energy into tiny volumes for incredibly short times. Accelerators like the Large Hadron Collider accelerate particles close to the speed of light before colliding them. The collisions generate high energies concentrated into small regions, effectively reaching high temperatures for extremely brief moments. But even with these collisions, the energy density is many orders of magnitude below what would be required to reach the temperatures near the Planck scale. Increasing the size of accelerators only scales energy linearly. To raise the temperature to the Planck level, one would need an accelerator the size of a galaxy or larger, and even that size would fall short. The amount of energy involved is so large that gathering it from any realistic source becomes impossible. Even if we harvested the output of every star in the galaxy for millions of years, the amount of energy needed would still exceed what could be delivered into the tiny region required for such high temperatures. Another challenge comes from the nature of gravity at extreme energy densities. If you try to concentrate too much energy into a small enough region, gravity becomes strong enough to collapse the region into a black hole. This collapse occurs long before reaching the temperature needed to explore the Planck regime. The threshold for black hole formation is determined by the mass energy content and the region over which it is spread. Once the energy within a volume reaches a certain density, the gravitational collapse becomes unavoidable. This is one of the clearest and strongest reasons why experiments cannot touch this depth. If you attempt to compress enough energy into a tiny space to reach extreme temperatures, the energy would warp space-time so much that it creates a horizon. All further attempts to increase the temperature would simply increase the size of the black hole rather than raise the temperature inside the region accessible to observation. This limitation arises from basic principles of general relativity. You cannot probe arbitrarily small distances with arbitrarily high energies, because the moment your energy surpasses a certain density, the curvature created becomes so strong that the region becomes causally isolated. Any information inside that region becomes unreachable. This behavior is not a matter of technological inconvenience. It is a fundamental constraint built into physics. The idea that measuring smaller scales requires higher energies works well until you reach the point where gravity intervenes. Beyond that, increasing energy does not give more information. It gives less. The region collapses, trapping information inside a horizon. Even if we ignored the collapse into a black hole, there remains the problem of containment. Generating extremely high temperatures requires confining particles within a tiny region. But as energy increases, particles move faster, approaching the speed of light. They would escape any containment system instantly. No known material could confine particles with energies that large. Even electromagnetic fields, which are used to confine plasma in fusion devices, cannot hold particles approaching Planck scale energies. The particles would simply pass through any barrier because the barrier itself would break down under the energy. The fields would distort, the structure would collapse. Nothing could resist the explosive behavior of such energy densities. The creation of extreme temperatures also requires extremely rapid interactions. In experiments, heat is produced by rapid collisions. But to reach the temperatures in question, particles must collide with such enormous energies that the fields required to accelerate them would need to be far beyond anything physically achievable. Accelerating a single particle to Planck energy would require field strengths that exceed the structural integrity of space-time. Even the vacuum has limits on how much field strength it can support before becoming unstable. At certain thresholds, strong electric fields tear apart vacuum, creating particle-antiparticle pairs. If you increase the field strength further, the vacuum itself becomes disrupted. Trying to accelerate particles beyond this point would cause the vacuum to break down, destabilizing the environment before reaching the desired energy. Another physical barrier arises from the amount of radiation produced. When particles accelerate, they emit radiation. As the acceleration increases, the radiation emitted becomes more intense. At extreme energies, the energy lost to radiation would exceed the energy being fed into the system. The particle would never reach the desired temperature because it would radiate away energy faster than it can be supplied. This radiation limit is another fundamental constraint that prevents reaching Planck scale temperatures. If one imagines circumventing the limitations of particle accelerators by compressing matter, instead, the situation does not improve. Compressing matter to extreme densities generates enormous pressure and heat. But even if you compress matter with the force of a supernova, the temperature remains far below what is needed. The moment you compress matter too far, neutron degeneracy and quark degeneracy resist further collapse. If you continue pushing, the matter collapses into a black hole. In either case, the temperature does not approach the Planck temperature, because gravitational collapse intervenes long before. Some might consider using extreme astrophysical phenomena as analogues for laboratory experiments. For example, the centers of neutron stars and regions near black holes produce enormous energy densities. But even these natural objects fall far short of the temperatures near the Planck scale. The highest temperatures accessible in the universe today are found in the aftermath of certain high-energy cosmic collisions, but they remain orders of magnitude too low. Even the earliest universe, fractions of a second after its beginning, did not reach the Planck temperature. The universe's temperature immediately after the earliest interval was high, but cooler than the Planck temperature because quantum gravitational effects limited the temperature achievable. This leads to another important point. The Planck temperature is not simply a temperature you can reach. It is a limit built into the structure of the universe. The Planck temperature marks the point where the energy of particles becomes so high and the curvature of space-time becomes so intense that the laws of physics as currently understood break down. Beyond that temperature, the concepts we use, energy, distance, time, temperature, lose meaning as currently defined. Approaching it requires interacting with domains where both quantum mechanics and gravity dominate equally. No experiment can push into that domain without collapsing under its own attempts to generate the conditions. Even if a machine were built with fictional materials strong enough to contain extreme energies, and fictional energies large enough to accelerate particles close to the Planck limit, and fictional technologies capable of holding those particles in a confined region, gravity would intervene. The energy would curve space-time so much that the region would pinch off. The experiment would vanish behind a horizon before any observation could be made. The attempt to access the Planck regime would prevent further access. The very process of trying to reach it would destroy the experimental setup. Another barrier arises from energy sourcing. To reach extreme temperatures, one must supply the energy from somewhere. The energy required to heat even a tiny region to the Planck temperature exceeds the entire energy output of known galaxies over billions of years. Even if one could gather that energy, transporting and delivering it into a region without losing efficiency would require violating conservation laws. The idea of tapping into vacuum energy or dark energy does not solve this, because those energies are distributed uniformly across space, not accessible in concentrated form for localized heating. There is also a limitation tied to the speed at which energy can be delivered. Energy transfer has limits imposed by causality. You cannot deliver energy faster than the speed at which signals propagate. Even if you had unlimited energy resources, delivering them fast enough to generate Planck-scale temperatures without the region expanding or radiating energy away is impossible. The energy would escape faster than it could be used to heat the region. These constraints highlight something important. The Planck regime is not just unreachable technologically, it is unreachable in principle. No known physical process outside the earliest instance of the universe can produce those conditions. It represents a boundary where the known laws lose their meaning. The temperature is not something that something can simply reach. It marks the transition where our current descriptions fail. This makes it fundamentally different from any temperature achievable in a machine. Because no experiment can reach this depth, physicists rely on indirect evidence. They consider how lower energy physics behaves as temperature increases. They extrapolate trends. They use mathematical frameworks like effective field theories, renormalization group flows, and symmetry principles to explore how forces behave at higher energies. They examine the patterns of unification emerging at energies far below the Planck scale. They look for clues in cosmic background radiation, in gravitational waves, in particle interactions, and in high-energy astrophysical events. These clues allow them to build models, test partial ideas, and refine understanding. But nothing replaces direct observation, and at these temperatures direct observation is not possible. Because the domain is inaccessible experimentally, theories must be built in a careful way. They must match everything we observe at lower energies. They must respect the constraints imposed by general relativity and quantum mechanics. They must remain mathematically consistent. These requirements significantly restrict what models can succeed. Yet despite the restrictions, none has provided a complete description of the Planck regime. This helps explain why quantum gravity remains unresolved. It is not simply difficult, it is inaccessible by experiment, meaning only theoretical consistency and indirect observations can guide progress. Reaching a point where experiments can no longer probe deeper forces physicists into an unusual position. In most areas of science, direct testing guides progress. You make predictions, you build tools, you observe results, and you update the theory. When studying temperatures close to the highest ones the universe can sustain, the usual process breaks down. There is no experiment capable of producing the required energies. No observation can be made of conditions approaching the Planck temperature. Even the environment of the early universe, though extremely hot, never reached this range for more than the tiniest sliver of time, and the traces left behind offer no direct details about the structure of reality at this scale. Yet physicists still work to understand what might happen when temperature climbs toward these unreachable heights. They do it by extending the theories we already have in ways that remain consistent with everything observed so far. These extended ideas act like lanterns illuminating a path through darkness. They do not reveal the landscape fully. They reveal outlines, possibilities, and shapes that give hints about what could exist at the edges of our understanding. One of the first lanterns people turn to is the idea of quantizing gravity. We know that quantum mechanics successfully describes all the other forces. We also know that gravity follows a classical description. This mismatch becomes problematic at extremely small scales or extremely high energies, where quantum effects should influence how gravity behaves. Attempts to quantize gravity begin by applying the same tools used for other forces, but when one tries to quantize spacetime curvature directly, the resulting theory becomes inconsistent. The equations diverge uncontrollably, the values blow up. Renormalization, which works beautifully in quantum electrodynamics and quantum chromodynamics, fails for gravity in its straightforward form. This failure led to the search for theories that avoid these divergences by modifying gravity's description. One of the earliest such attempts was string theory. Instead of treating particles as points, string theory describes them as tiny vibrating strands. These strands have different vibrational modes, and each mode corresponds to a type of particle. The idea solves many of the infinite quantity problems that arise when trying to quantize gravity. Strings cannot interact at infinitely small distances the way point particles can, because a string always has a finite size. This limitation smooths out interactions and removes the infinities that break ordinary quantum gravity attempts. Another appealing feature is that one of the vibrational modes corresponds naturally to something that behaves like a graviton. This gives string theory a way to unify gravity with the other forces. However, the theory requires additional spatial dimensions. These extra dimensions must be compactified, hiding them at scales too small to observe. The mechanism for compactification introduces new questions, and the theory has a vast landscape of possible configurations. This makes it challenging to produce concrete predictions tied to observable phenomena, but it remains one of the most developed and mathematically consistent attempts to describe physics near the Planck temperature. Another lantern comes from loop quantum gravity, which takes a different approach. Instead of extending particle-based ideas, loop quantum gravity modifies the structure of spacetime itself. The theory treats spacetime as composed of discrete units, woven together in a network of loops. Distances and areas are quantized. This removes the notion of infinitely small points, providing a foundation where spacetime has a minimum scale. At this scale, geometry becomes granular rather than continuous. This granularity prevents the infinite curvature that appears in classical general relativity near singularities. It also changes how gravity behaves at very small distances. The equations of loop quantum gravity predict that spacetime cannot shrink below a certain minimum volume. This offers a possible replacement for singularities, suggesting that the universe might have experienced a bounce rather than an initial point of infinite density. While this idea is compelling, loop quantum gravity remains incomplete. It lacks a clear mechanism to include the full range of matter and forces. Still, it provides a framework in which geometry itself carries quantum properties, shaping how gravity behaves at high temperatures. Another idea focuses on asymptotic safety. This approach proposes that gravity might be well behaved at high energies after all, provided one looks at it through the lens of renormalization group flows. In this picture, gravity becomes weak at extremely small distances due to the way its coupling constant changes with energy. Rather than diverging or becoming uncontrollable, gravity might approach a fixed point where its behavior stabilizes. This fixed point would prevent infinities from appearing. If true, the theory could provide a complete description of quantum gravity without requiring additional dimensions or radically different mathematical structures. Research in this area continues, but so far the evidence remains incomplete. It provides a potentially elegant solution, though not one that has been universally accepted. Ideas also emerge from approaches that treat gravity not as a fundamental force, but as an emergent phenomenon. In this view, gravity arises from deeper microscopic interactions, much like temperature arises from the collective motion of atoms. If gravity is emergent, then describing it at high temperatures might require understanding the underlying degrees of freedom that give rise to space-time. These ideas are inspired by analogies with thermodynamics and condensed matter physics. They suggest that what we see as geometry might be a large-scale pattern, with the true constituents remaining hidden. If this is correct, the Planck temperature might correspond to a phase transition of space-time itself. But without knowing the degrees of freedom responsible, the theory cannot be tested. It remains a guiding idea rather than a complete model. Another lantern comes from holography. The holographic principle suggests that information in a volume of space can be represented on its boundary. This idea was first proposed in the context of black hole entropy. The entropy of a black hole scales with the area of its event horizon rather than the volume inside. This result inspired the notion that space-time and gravity in higher dimensions might be described by quantum field theories on lower dimensional boundaries. The holographic principle provides a powerful framework called the AD-CFT correspondence. While this correspondence is based on a type of space that does not match our universe perfectly, it offers insights into how gravity and quantum mechanics might be related. It hints that gravitational physics at high temperatures could be equivalent to behavior in a strongly interacting quantum field system at lower dimensions. This duality provides computational tools that allow certain aspects of extreme temperature behavior to be studied indirectly. There are also ideas involving causal dynamical triangulations, which describe space-time as a structure built from fundamental building blocks arranged in different configurations. By summing over possible configurations, one tries to recover the behavior of large-scale space-time from discrete components. This approach treats geometry as something that emerges from combinatorial rules. Some results suggest that at small scales, space-time might have fewer effective dimensions. This reduction in dimensionality could help resolve infinities by altering how gravity behaves at high energies. Though still under development, the idea offers another angle on how space-time might behave when approaching the Planck regime. Some theories propose that space-time might not be a fundamental entity at all. Instead, it might arise from the entanglement structure of quantum fields. If space-time is built from relationships between quantum states, then the Planck temperature might be the threshold where these relationships shift dramatically. In such models, geometry is not something separate from the quantum fields, but something woven from the connections between them. This perspective could change how temperature interacts with the underlying structure. But this idea is speculative, and the mathematical tools needed to develop it fully remain under construction. Supersymmetry provides another lantern. It proposes that every particle has a partner with different spin properties. If supersymmetry exists, then at high temperatures the symmetric structure would manifest clearly before breaking at low energies. Supersymmetric theories often provide more stable high-energy behavior, making them attractive candidates for unification. They also integrate naturally into string theory, but experiments have not yet found evidence of supersymmetric particles. Without experimental confirmation, supersymmetry remains a theoretical tool, useful for constructing models even if the physical world does not use it directly. All these ideas, string theory, loop quantum gravity, emergent gravity, asymptotic safety, holography, causal structures, and supersymmetry, attempt to fill the gap left by our inability to probe directly into the Planck regime. They do not agree with each other. Some are mutually incompatible. Some require assumptions that have not been confirmed. Yet each provides a model that avoids the breakdown of physics at extremely high temperatures. Each offers a structure in which forces could unify smoothly. Each prevents infinities from taking over, and each allows the possibility of describing a universe where temperature, gravity, quantum mechanics, and space-time merge into a single consistent framework. These theoretical lanterns also guide research into the earliest universe. Even though the Planck temperature could not be reached directly even in the universe's first moments, the temperature approached it closely enough that quantum gravitational effects became important. When studying the earliest cosmic behavior, physicists use these theories to predict how fluctuations evolved, how expansion unfolded, and how forces separated. While none of the theories have been confirmed, they provide tools that can approximate the behavior of systems near the edge of comprehensibility. Another valuable point about these theories is that they reveal patterns that appear across different approaches. Many models predict that spacetime becomes discrete at small scales. Others suggest that the number of effective dimensions decreases at high energies. Still others argue for a unification of forces or a smoothing of interactions. These patterns hint at deeper principles. Even without knowing the exact structure, the convergence of different ideas towards similar features suggests that certain traits may be essential. Theories differ in details, but they agree that the smoothness of space-time must break down. They agree that gravity must change its behavior. They agree that new symmetries might emerge at high energies. They agree that the familiar descriptions of physics cannot stretch indefinitely. Because direct experiments are impossible, physicists test these ideas in indirect ways. Some use high-energy collisions to look for deviations from expected behavior. Others study black hole entropy. Others analyze cosmic microwave background data for traces of early universe behavior that might point toward one theoretical model or another. Each clue is small, but each adds a piece to the puzzle. The lanterns reveal possibilities, but not certainty. Yet they guide research, keeping it grounded in mathematical consistency and aligned with observed reality. Moving upward from the ideas that theoretical models offer, the attention naturally turns to what the highest possible temperature actually tells us about the structure of the universe. The Planck temperature, sitting at the top of the scale, is more than just a number. It marks the boundary where the combined framework of general relativity and quantum field theory can no longer be stretched further. At temperatures below this threshold, even when the environment is extreme, there are ways to describe what happens using the familiar tools of physics. But as the temperature rises toward the Planck scale, the assumptions built into those tools stop working. Instead of being just another extreme point, the Planck temperature becomes a signpost. It suggests that physics has deeper layers, and these layers do not reveal themselves until the universe is pushed toward conditions where the energy density is so high that space-time and quantum fields behave in ways that current theories cannot fully capture. Starting with the simplest explanation, the Planck temperature is the point at which the energy of individual particles reaches the Planck energy. This energy is defined by combining the constants that appear in quantum mechanics, relativity, and gravitation. These include Planck's constant, which governs quantum behavior, the speed of light, which limits the propagation of information, and Newton's gravitational constant, which influences how matter curves space-time. When combined, these constants produce a set of quantities that reflect the scales at which our descriptions must change. At the Planck temperature, the energy of a particle is so large that its gravitational influence becomes comparable to its quantum behavior. This is where the known theories contradict each other. One cannot treat space-time as smooth, yet one cannot treat energy as if it exists on a fixed background either. This mutual contradiction means that neither theory alone is reliable. The existence of a temperature where these contradictions appear tells us that the universe must operate under rules that unify or replace the current ones. That is the first hint at new physics. No matter how complex the standard model becomes or how many corrections general relativity includes, neither can explain the environment near the Planck temperature on their own. The fact that they both fail at the same point suggests that there must be a deeper framework that resolves the problem. This deeper framework is not something we've observed directly. It is something inferred from the inconsistencies that appear as the temperature climbs toward the Planck scale. The Planck temperature also hints at new physics through the breakdown of the concept of distance. At lower energies, distances can be defined using classical geometry. You can measure how far apart 2 points are or how long an object is, but at temperatures near the Planck scale, the fluctuations in spacetime become large enough that distance loses meaning. It becomes impossible to define 2 points as being a definite distance apart because the geometry changes too rapidly. This absurd situation, where even the most basic measurement stops making sense, indicates that our understanding of spacetime as a continuous field fails. That failure suggests that spacetime likely has a deeper structure. Perhaps it is discrete, or emergent, or derived from something more fundamental than geometry. The Planck temperature tells us that whatever this deeper structure is, it becomes dominant at extreme energies. Another way the Planck temperature points toward new physics lies in the loss of particle identity. At ordinary temperatures, particles have stable masses and charges governed by well-understood mechanisms. But as the temperature increases, the parameters that define particle behavior shift. The Higgs field changes, particle masses vanish, symmetries that are broken at low energies become restored. The idea of a particle as a stable excitation becomes unreliable. At the Planck temperature, the shift is so dramatic that even the meaning of a particle becomes questionable. The concept of a particle is built on having a background geometry and a stable field configuration. Without those, the distinction between a particle and a fluctuation becomes unclear. This breakdown suggests that matter as we understand it is not fundamental. The Planck temperature shows the limits of the particle-based description. Whatever exists at these temperatures might not consist of particles at all. It might instead take the form of something more basic, from which particles arise only at lower energies. If particles emerge from deeper structures, then those deeper structures must be part of any complete theory. The Planck temperature is the scale at which this emergence process becomes visible. The Planck temperature also highlights the limits of thermodynamics. Temperature, at its core, is a measure of the average energy per degree of freedom in a system. It works well when the system has a large number of degrees of freedom behaving statistically, but near the Planck scale it becomes unclear whether the system can be described by degrees of freedom in the usual sense. If spacetime itself fluctuates, if particles do not exist in stable forms, and if forces merge into unified interactions, the concept of degrees of freedom changes. Thermodynamics depends on equilibrium, but equilibrium may be impossible because fluctuations occur too quickly. This raises the possibility that temperature in the usual sense cannot be defined above the Planck scale. If temperature cannot be defined, then thermodynamics must be revised for these conditions. This points to another region of new physics. Thermodynamics has been extraordinarily successful at describing systems from everyday life all the way up to early universe plasmas, but its breakdown at the Planck temperature suggests that the laws governing heat, entropy, and energy distribution must be extended. Something deeper must dictate how energy behaves when spacetime no longer provides a stable background. Turning to gravity, the Planck temperature also marks the point where general relativity loses its validity. This is not because general relativity becomes mathematically meaningless, but because the assumptions behind it break. The theory assumes a smooth spacetime with well-defined curvature. At these temperatures, quantum fluctuations make that curvature bounce unpredictably. Gravity must be described in a quantum way. The existence of a temperature where spacetime becomes a fluctuating environment indicates that gravity must have quantum properties that go beyond general relativity. This conclusion is a major hint at new physics. It suggests that all attempts to combine quantum mechanics and gravity must converge toward a consistent description at the Planck scale. If such a description exists, it would unify the two frameworks. but because no single theory has been confirmed, the Planck temperature serves as a reminder that gravity and quantum mechanics are currently incomplete in isolation. Another important clue comes from the behavior of black holes. The temperature associated with Hawking radiation increases as the mass of a black hole decreases. In the limit where a black hole becomes extremely small, its temperature approaches the Planck scale. This suggests that the smallest black holes would radiate at temperatures where quantum gravity must dominate. The connection between black holes and the Planck temperature implies that the microscopic structure of space-time must govern the final stages of black hole evaporation. This stage cannot be described by general relativity or quantum field theory alone. The Planck temperature marks the point where black hole physics and quantum gravity collide. The relationship between the Planck temperature and black hole evaporation also hints at the possibility of new effects. For instance, the endpoint of evaporation might not be a complete disappearance. It might leave behind a stable remnant or transition into a different form of object. These outcomes depend on how quantum gravity behaves. The Planck temperature acts as a guide, indicating that the physics governing these possibilities must operate at this energy scale. There is also another hint from the early universe itself. Though it did not remain at the Planck temperature for any measurable duration, the universe passed through a stage where temperatures approached it. This means that the earliest moments were governed by physics we cannot describe with current theories. The fact that the universe emerged from that stage in an orderly manner, with stable particles and forces forming as temperatures lowered, suggests that the unknown physics at the Planck scale must be orderly enough to lead into the world we see today. That alone is a hint that whatever new physics lies there must be consistent with the emergence of classical reality. The smoothness of the cosmic microwave background provides another clue. The uniform temperature, along with the tiny fluctuations embedded in it, show that whatever happened near the Planck scale left a subtle imprint. The fluctuations reflect quantum behavior that was stretched across cosmic distances. This suggests that the new physics governing the Planck regime must be capable of producing fluctuations that evolve predictably when stretched by cosmic expansion. The fact that the universe became smooth, yet not perfectly uniform, hints that quantum gravitational effects at the Planck scale shaped the seeds of later structure. Another important clue is the unification of forces. The electroweak unification at lower energies shows how symmetry breaking separates interactions. Grand unified theories predict that at high enough energies, the strong, weak, and electromagnetic forces merge. But gravity remains separate. The Planck temperature is the scale where gravity may naturally join the unification. This suggests that any full theory must include a mechanism for force unification at extreme temperatures. The existence of a temperature where all forces could be unified is itself a hint that new physics must include symmetry principles larger than those currently used. Looking at the mathematical structure of the constants that define the Planck temperature also provides hints. These constants combine in ways that suggest deeper connections. The Planck temperature is not an arbitrary number. It arises from fundamental constants whose values appear finely tuned for a universe capable of structure. The fact that the Planck scale emerges naturally from the combination of constants points toward the possibility that these constants are not independent. They may derive from a deeper underlying theory whose parameters dictate the values we observe. If that theory exists, the Planck temperature represents the energy scale where its structure becomes visible. Even the concept of quantum foam, which appears at temperatures near the Planck scale, suggests new physics. Foam-like fluctuations indicate that geometry is not fundamental. If geometry emerges from something more basic, then the Planck temperature is the threshold where that emergence becomes apparent. This means that the structure of space-time is not built in, but arises from deeper principles. Those principles must govern the behavior of fields and forces in ways that unify them at high temperatures and separate them at low temperatures. Another clue comes from the behavior of information. Quantum mechanics is built on precise rules for information flow. General relativity, however, becomes ambiguous about information near singularities. At temperatures where both theories fail individually, information must be governed by rules consistent across quantum and gravitational domains. These rules must be part of the new physics lying beyond the Planck scale. The hints come from phenomena like black hole entropy and holographic principles, suggesting that information is stored in ways tied to geometry. This connection implies that any new physics must describe geometry and information together. The Planck temperature also hints at limits to how energy can be distributed. If attempts to exceed this temperature cause collapse or unpredictable behavior, this suggests that the universe has an upper bound on energy density. An upper bound implies that the structure of space-time prevents infinite energy from being concentrated. This limitation suggests that energy cannot be arbitrarily increased, a hint that new physical rules impose constraints beyond those of conventional thermodynamics. All these clues taken together point toward new physics that must emerge at energies near the Planck scale. The Planck temperature acts as a boundary the universe has drawn. It does not allow current theories to pass beyond it. Instead, it forces us to recognize that below this threshold, the universe behaves according to the rules we understand. Beyond it, those rules fail, guiding us toward a more complete description that has yet to be discovered. Reaching this point in the climb brings the temperature scale to the very limits of what current physics can follow, and stepping gently into this last long stretch means accepting that the descriptions used so far are already working at their full capacity. Each range of temperature we pass through had a structure that could be traced with the tools of established theories. Even when the behavior of particles blurred, or forces merged, or geometry fluctuated, the rate of change still allowed some kind of mathematical expression to describe what happened step by step. But as the temperature approaches the upper boundary, where the known laws reach their limit, the picture becomes less about extending the rules and more about acknowledging the place where they must yield to something not yet written. Moving into these closing thoughts means letting the ideas settle naturally at that border, without treating the frontier as an end and without giving final statements, because the story continues beyond what can currently be described. Starting from the nature of the temperature itself, every point on the scale below this region still allowed temperature to hold a clear meaning. One could speak about equilibrium, average energy, and the behavior of particles distributing energy through collisions or field interactions. But nearing the upper limit, temperature becomes harder to define. The systems that support equilibrium stop behaving in the usual way. The fluctuations occur too rapidly for any averaging process to hold. The idea of a degree of freedom becomes strained, yet the concept remains useful enough to mark the energy scale where the usual behavior stops being trustworthy. This contrast between temperature remaining a helpful quantity and temperature losing its firm foundation serves as one of the clearer signs that something deeper must take over. Considering gravity at this boundary reinforces the same idea. Gravity's familiar behavior is rooted in the assumption that space-time is smooth enough for curvature to be defined precisely. In ordinary conditions, that assumption holds beautifully, even in environments with strong curvature like near large black holes or in regions with compact stars, space-time remains smooth. But near the highest temperatures, smoothness stops being reliable. The large energy densities stretch and distort the geometry, and quantum fluctuations force the curvature to oscillate on tiny scales. This leaves gravity without the steady form used to describe it at low temperatures. The transition does not imply that gravity disappears. It signals that gravity must be understood differently at these extremes. That difference cannot come from minor adjustments. It requires something entirely new, and that need for a new description becomes another way the temperature hints at deeper physics. The behavior of particles continues to add to this picture. At lower temperatures, identifying a particle is straightforward. It is an excitation of a field with a mass, a charge, and a behavior under forces that remain stable. But at higher temperatures, the features tied to mass vanish as the Higgs field changes. Charges remain, but their significance changes as forces unify. The identity of each particle becomes blurred. Near the highest temperatures, the combination of geometric fluctuation, force unification, and rapid interaction makes the concept of a particle lose its usual meaning. Instead of thinking about particles as identifiable excitations, the meaningful thing becomes the underlying structure that creates them at lower energies. This underlying structure remains invisible at everyday temperatures, and temperatures near the Planck scale make it clear that the structure must exist. The identity loss is not an end. It signals a deeper pattern, one that ordinary physics only reveals indirectly. Another thread that guides thought at this boundary comes from how fields behave. In ordinary quantum field theory, fields exist on a fixed background. Their fluctuations can be large or small, but the spacetime that supports them is stable. Near the highest temperatures, the background stops being stable. The spacetime fluctuations affect the fields, and the fields affect the fluctuations. They merge into a single dynamic environment where the separation between field and geometry stops functioning. This merging is not a random collapse into disorder. It is a natural progression of what happens when energy levels rise to the point where the assumptions of field theory meet the assumptions of relativity, and both reach their limits. The merging implies that neither set of equations can stand independently. A new framework must describe them together. That need becomes one more quiet suggestion that deeper physics shapes the environment, even though the details remain unknown. Looking at the behavior of the universe itself provides another layer of insight. The earlier stages of cosmology demonstrate that the universe passed through temperature ranges, where ordinary physics breaks down. The fact that it transitioned smoothly into the temperatures where particles, forces, and fields behave as we observe today means the unknown physics at the higher scale must have followed rules consistent enough to guide the universe forward. This consistency shows that whatever lies beyond the descriptions used now cannot be chaotic or arbitrary. It must have structure strong enough to produce a stable universe once the temperature falls. The earliest cosmic expansion also stretched quantum fluctuations across vast distances. These fluctuations seeded the structures that would appear much later. That stretching of tiny variations into large-scale patterns shows that quantum gravitational effects carry information capable of influencing the universe long after those temperatures fall away. This influence acts like an imprint left behind by physics that cannot be directly observed, but that still shapes everything around us. One of the more subtle ways that the highest temperature hints at new physics appears when considering information. At ordinary energies, information is handled by quantum rules with perfect precision. These rules govern how systems evolve, how probabilities behave, and how outcomes relate to one another. But near the Planck temperature, the fabric carrying information loses the clarity needed to follow the rules precisely. If time and distance cannot be defined with stability, the usual description of information flow must change. This does not suggest that information becomes meaningless. It suggests that the concept of information is tied to structures that exist beyond space-time as commonly described. Quantum mechanics preserves information perfectly. General relativity allows conditions where information seems to disappear. Resolving this tension likely requires new physics, and the fact that the Planck temperature is the point where the tension becomes unavoidable shows that this scale marks a boundary where these different ideas must merge. The merging of forces plays another role here. At energies far below the Planck scale, the strong, weak electromagnetic and gravitational forces operate separately. Their behaviors differ, their strengths differ, and the ways they interact with particles differ. But the unification of the electroweak force at high energies provides an example of how two forces that seem completely unrelated can merge into a single entity. Grand unified theories propose that all the non-gravitational forces may also merge at still higher energies. If gravity joins them at an even higher temperature, then the Planck scale becomes the point where such merging must occur. The fact that unification appears in the behavior of forces as temperature rises shows that the Planck temperature marks a natural extension of that pattern. The behavior does not form a conclusion. It forms a continuity that points to new physics beyond this boundary. Even the methods physicists use to infer the existence of deeper layers show how the Planck temperature guides understanding. Whenever a theory stops working at a certain scale, it is because the assumptions behind it no longer hold. This pattern has occurred repeatedly in the history of physics. Newtonian mechanics stops working at speeds near the speed of light. Relativity stops working when quantum effects become significant. Quantum field theory stops working when gravity becomes strong at tiny distances. Each time a framework reaches its limit, a broader theory emerges. The fact that both quantum mechanics and general relativity fail together at the Planck scale means that the broader theory linking them must become visible at this point. Even though the broader theory is not yet known, the Planck scale marks the place where it must become active. The temperature does not represent a conclusion. It represents the threshold of a deeper structure still unfolding. The constants forming the Planck scale also offer direction. They combine in ways that show that the scale is not arbitrary. The Planck temperature arises from a combination of constants tied to quantum mechanics, relativity, and gravitation. This combination suggests that the boundaries between these areas of physics are not accidental. They meet at a common point defined by the behavior of nature itself. Whenever natural constants combine into a meaningful scale, it usually marks a place where something fundamental happens. The Planck temperature marks such a place, telling us that the transition into deeper physics is not imposed artificially. It comes from the most basic properties of the universe. The gradual breakdown of space-time smoothness, the weakening of gravity's separate identity, the loss of stable particle features, the merging of forces, the instability of temperature itself, and the behavior of fluctuations all build toward the same suggestion. They show that reaching the Planck temperature is not simply reaching a hotter environment. It is reaching the point where the structures used to describe the universe must be rebuilt from the ground up. The new structure must contain quantum fields, geometry, gravitation, information flow, and force behavior all within one consistent description. Another layer comes from the behavior of black holes. Their evaporation through Hawking radiation touches the Planck temperature in the final stages, meaning that the last moments of a black hole's existence are governed by physics beyond the current theories. The information stored in black holes must be handled by whatever new physics emerges at these scales. The fact that black holes reduce their mass over time, pushing their temperature upward, means that the Planck scale is directly tied to the end states of these objects. This is another clear signal that the highest temperature acts as a marker where the deeper structure of the universe becomes essential. As we remain near this boundary, the focus shifts not to concluding anything, but to noticing how all these different clues point toward the same need: a framework that can describe quantum behavior, gravitational effects, and extreme temperatures consistently. The Planck temperature does not provide this framework. It simply marks the place where it must appear.